Good morning to you all. I'd like to extend a warm welcome to our Vice Chancellor, Dean Faculty of Science, former Vice Chancellors, former Deans, Deans of other faculties, Council members, Conference Chair, General Chair, keynote speakers, invited speakers, professors, senior lecturers, presenters, participants, students, and all the invitees to the VINGNANAM Research Conference 2024. Your presence here today highlights your commitment to research and innovation for sustainable and resilient future. The Faculty of Science, University of Jaffna, organizes VINGNANAM Research Conference as one of the satellite conferences of Jaffna University International Research Conference 2024. It aims to provide an open forum for national and international researchers from diverse disciplines to disseminate their research findings, share ideas, and experiences.
Good morning again. And now we are about to commence our event by lighting the lamp of knowledge and wisdom. This is a symbolic moment that signifies the dispelling of darkness and igniting of thought and enlightenment. To perform this honored task, I would like to invite our Vice Chancellor, Professor S. Sri Satnaraja, and Dr. S. Shuthanandan, Senior Research Scientist, Pacific Northwest National Laboratory, and Research Professor, Aerospace and Mechanical Engineering Department at the University of Texas, USA. And also Dr. Sabesan Sidambaranathan, Founder and President at Pervas ID and Fellow at Cambridge University Curtin College, United Kingdom. And Dr. N. Nanda Nandakumar, Chief Scientific Officer at A9 Health at US. And also I would like to invite Dr. S. Sivanandan, Senior Scientist at Peter MacCallum Cancer Centre in Australia. Dr. T. Udyashankar, Senior Lecturer, Department of Computer Science and Engineering, University of Moratuwa. At the same time, I would like to invite Mr. K. Suresh Kumar, Bursar, University of Jaffna. And now I would like to invite Mr. Kantiban, Registrar, University of Jaffna. At the meantime, I would like to invite Professor N. Kankadaran, Dean Management Studies and Commerce, and also Professor R. Surendra Kumaran, Dean Medicine. Professor S. Raghuraman, Dean Arts. Mr. S. Padmanabhan, Dean Hindu Studies. At the same time, I would like to invite Mr. S. Sivaruban, Dean Sir Ponnambalam Ramanathan, Faculty of Performing and Visual Arts, and Professor S. Bhagirathan, Dean Agriculture. Now I would like to call upon a student representative to light the traditional oil lamp. At the meantime, I would like to invite Conference Chair Professor S. N. Surendran to light the ceremonial oil lamp. And eventually, I would like to invite our Dean Science. Sir, please join us to the stage to light the traditional oil lamp. Thank you, sir. Thank you, all of you.
A heartfelt thanks to our esteemed guests for leading this auspicious beginning. As the lamp's light continues to radiate throughout the day, let it remind us of our collective commitment to knowledge, harmony, and progress. With this luminous start, we now officially declare the event open and proceed with our planned schedule.
Now, I am honored to invite to the main head table our esteemed Vice Chancellor, Professor S. Sri Satkunaraja, University of Jaffna, and also General Chair, Jaffna University International Research Conference 2024. At the meantime, Dr. S. Shuthanandan, Senior Research Scientist, Pacific Northwest National Laboratory, and Research Professor, Aerospace and Mechanical Engineering Department at the University of Texas at El Paso, United States. Also, Dr. Sabeshan Sidambaranathan, Founder and President at Pervas ID, and a Fellow at Cambridge University Curtin College, United Kingdom. And our invited speakers, Dr. N. Nanda Nandakumar, Chief Scientist Officer at A9 Health USA. Also, Dr. S. Sivanandan, Senior Scientist at Peter MacCallum Cancer Centre in Australia. Dr. T. Udaya Shankar, Senior Lecturer, Department of Computer Science and Engineering, University of Moratuwa. Professor P. Ravirajan, Dean, Science, General Chair of the VINGNANAM Research Conference 2024. And Professor S. N. Surendran, Conference Chair of VINGNANAM Research Conference 2024.
Now, to officially inaugurate our conference, I would like to invite a key person whose dedication and hard work have been instrumental in making the VINGNANAM Research Conference 2024 a reality. It is my pleasure to welcome the Secretary of the conference, Mrs. Sudarshini Satyaruban, to deliver the welcome address.
Our respected Vice Chancellor, General Chair of the Jaffna University International Research Conference for the year 2024, Professor Sri Sarkanaraja. Esteemed guests, including Dean Medicine, Dean Arts, Dean Hindu Studies, Dean Agriculture, Dean Management Studies and Commerce, Dean Sir Pon Ramanathan, Faculty of Visual and Performing Arts, Bursar of the University, Registrar University of Jaffna, Council members, sponsors, NOPAD Project and National Science Foundation, distinguished speakers, conference chairs, professors, senior lecturers, temporary lecturers, demonstrators, presenters, non-academic staff, and my dear students. Very good morning to you all. On behalf of the committee, it's my absolute pleasure to extend a warm welcome to the VRC 2024 conference. With great pleasure and immense pride, we gathered here today to embark on a journey of knowledge sharing, collaboration, and innovation. This conference serves as a platform for us to delve into realms of scientific research and technological advancement. And I am honored to see such a diverse and esteemed audience joining us today. As we commence this conference, I'm reminded of Albert Einstein's words. The important thing is not to stop questioning. Curiosity has its reason for existing. With this sentiment in mind, let us embrace the spirit of curiosity as we engage in insightful discussions and thought-provoking sessions throughout this event. I extend my heartfelt gratitude to all the speakers, session chairs, and organizers who have worked tirelessly to bring this conference to fruition. Your dedications and expertise have laid the foundation for an enriching the intellectually stimulating experience for all of us. I encourage each of you to actively participate, exchange ideas, and forge new connections during this conference. Ladies and gentlemen, once again, I welcome you all to the VRC conference. Thank you.
Thank you, ma'am, for your inspiring words and for setting the tone for this conference. Now, it's my honor to invite a truly remarkable individual who has been the backbone of this conference, working tirelessly to make it success. Please join me in warmly welcoming the conference chair, Professor S. N. Surendran, to the stage.
The Vice Chancellor and Co-Chair of the Jaffna University International Research Conference, Dean of the Faculty of Science and co-chair of the VINGNANAM Research Conference, esteemed keynote speakers and invited speakers, deans from other faculties, distinguished guests, researchers, and my colleagues. It is with immense pleasure and a deep sense of honor that I stand before you today as the chair of the prestigious conference. The 2024 VINGNANAM Research Conference marks a landmark event bringing together brilliant minds from diverse fields under the theme Research and Innovation for a Sustainable and Resilient Future. This theme is not just a call to action, but a reflection of our collective responsibility to ensure that our research and innovation contribute to a society that is sustainable, resilient, and capable of meeting the challenges of the future. Today, the scientific community is more united than ever, recognizing the importance of interdisciplinary research in addressing the complex issues our society faces. From the physical to biological sciences, integrating knowledge across disciplines is essential to promoting a healthier and safer world, especially we navigate rapid technological advancement that continue to shape our lives. The Faculty of Science takes great pleasure or great pride in organizing this conference, reinforcing our commitment for fostering collaboration and knowledge sharing among researchers from various scientific disciplines. We are privileged to have with us today an outstanding lineup of speakers, some of whom are distinguished alumni of our university. These individuals have excelled in their respective fields and will deliver keynote and invited talks that promise to inspire and challenge us. This year's conference holds special significance as it coincides with the Golden Jubilee celebration of both the university and the Faculty of Science. This milestone adds a new dimension to our gathering, reminding us of the rich legacy of excellence we inherit and the future we are building together. As a conference chair, I would like to express my sincere gratitude to our Vice Chancellor, the Dean of the Faculty, and the dedicated members of the conference committee. Their unwavering support, guidance, and hard work have been instrumental in making this event a success. I also extend my deepest thanks to all of you for your presence here today. Your participation is a statement or testament to our commitment to advancing scientific knowledge and making a meaningful impact on our society. I am confident that the discussions and deliberations that will take place today will be both enlightening and enriching. Once again, thank you for being here, and I sincerely hope that you find today's proceedings both valuable and inspiring. Thank you.
Thank you very much, sir, for your insightful and inspiring words. It is my great pleasure to invite a dedicated leader who serves as the Dean of the Faculty of Science. His invaluable contributions have greatly advanced key collaborations and faculty development. Please join me in welcome the General Chair, VINGNANAM Research Conference 2024, Professor P. Ravirajan, to deliver his address.
Our respected Vice Chancellor, Professor Sri Sakuraja, and also the co-chair of the Youth 2024, our keynote speakers and also invited speakers, and conference chair, deans of the faculties, heads of the department, and my dear colleagues and students. It is my great pleasure to have this opportunity to welcome you all to this conference, which is organized by the Faculty of Science as a part of the conference of International Conference of the University, Youth 2024. Under the theme of Research and innovation for sustainable and resilient future. This significant event actually coincides with the Golden Jubilee of the faculty, celebrated under this theme. This milestone provides us with an opportunity not only to celebrate our achievement with pride, but also look ahead with confidence, reflecting our remarkable journey over the 5 decades and thoughtfully planning our path ahead. Over the past 50 years, the Faculty of Science has cultivated a strong research and innovation, actively engage both academics and students. Research is deeply embedded in our curriculum, and our faculty members collaborate extensively with renowned universities around the globe, and enriching our academic environment and expanding our global impact. Reflecting on our journey, the first 2 decades were marked by significant development and progress as a faculty successfully overcome numerous challenges. Despite heavy teaching commitments and limited experimental facilities, our dedicated staff pursued conducting much of their works during their overseas sabbaticals, first 2 part of the decades of this service. Our senior academics were actively engaged in research while abroad, maximizing their limited time in Jaffna to prepare publications. These early efforts laid a solid foundation for the continuous delivery of quality science education and research. In the last 2 decades, the faculty has significantly accelerated its progress, securing substantial grants from national and international funding agencies through strong partnership with prestigious universities abroad. These collaborations have enabled us to establish state-of-the-art research laboratories and conducting pioneering research and publishing numerous papers in high-impact factor journals. Today, our contributions account for over 1/3 of the university index publications, and our achievements have been recognized with numerous national and international awards. We are also proud that a good number of staff have successfully filed and have been awarded research and technology patents. Our faculty periodically organize research symposium and conferences, providing a valuable platform for our researchers to present and exchange their findings in both pure and applied sciences. To commemorate the 50 years of contribution to the science education and research, so we have invited distinguished scientists from around the world, including our extreme alumni, to deliver keynote and invited speech. So on behalf of the organizing committee and the faculty, I extend my heartfelt appreciation to our speakers for dedicating their time and resource to share their insight with us. I also wish to commend the dedication and hard work of our organizing committee, members of the organizing committee. Those efforts have brought VRC 2024 to fruition, and despite their demanding commitments. I would also like to thank the VC Media unit for providing live coverage of the inaugural session of this conference. Finally, I would like to express my deepest gratitude to the National Science Foundation and also the Norwegian Directorate for Higher Education and Skills under the Higher Education and Research Project for their generous financial support in organizing this conference. Thank you all for being here. I look forward to inspiring presentation and productive discussions that unfold during this conference. Thank you very much.
Thank you, sir, for your valuable and timeless insights. Now, it's my great honor to welcome our Vice Chancellor, who has made remarkable contribution to the university and the faculty, particularly in advancing academic excellence, fostering research innovation, and enhancing student engagement. Please join me in welcoming the General Chair of JUICE 2024, Professor S. Sri Satguru Raja, to deliver his address. Sir.
சிற்றம்பலம் ஆனந்தமாய் என் அறிவாய் நிறைந்த அமுதவுமாய் ஆனந்தமான வடிவுடையாள் மறை நான்கினுக்கும் தானந்தமான சரணார விந்தம். So we call Mother Earth. So one of the most celebrated cosmic entity in this universe. We study cosmology. Now our keynote speaker Sudanandan from Space Agency. So we explore all the universe to see anything like this planet. No evidence for water, no evidence for anything. So this planet is made of terrestrial and aquatic. Today in the high table, those who are decorating are those who have climbed Everest. So being here from 1979, more than 45 years, I witnessed something different in the annals of the faculty. For different reasons. Anandamaya and Arivai. So the Vingnanam is an ancient word. Even in our existence, our constitutional position of the body, the ancient wisdom says we are Annamaya Kosam, made of flesh and bones. There is a Pranamaya Kosam, there is air circulate in our body. There are 72,000 sort of nerves are there, even yet to be found by our anatomy. Counting. They have some other sub-level they have understood. Then we have Manomaya Kosam. We have a psychology department in the arts faculty, medical faculty, and all kind of AI working now, try to mimic what we have been doing. So Mano-mind. Yes, then Vingnanamaya Kosam. So we have analytical living entity. We are analytics. Now the big data business is analytics. So we have a Vingnanamaya Kosam. So the science faculty is engaged in that type of endeavors. So when we were young, came here, then we see two main division of the Faculty of Science, that is the physical sciences and the biological sciences. Today Nanda is here to talk about the biological aspect, not the balance is not maintained. All our others are nobelists there, entomologists and microbiologists. So other computer scientists are there, radiologists are there. So we heard about Sabeshan when he was doing excellence in the A-levels. Then we know he was going to go to Cambridge. Then another man he went to Cambridge is Nishan. So he came here a couple of months ago and gave lectures, and he's the Vice Chancellor of Leicester University. So he can come to Cambridge, and he was the first one telling me about the spin-off companies. So he's a professor there, but he has been encouraged by the Cambridge do some spin-off companies. I know by chatting with him, he has developed some microwave communication stuff. So Cambridge encouraged him, be in the payroll, but go for developing startups. So they call it spin-off companies. So this is the agenda now. Eastern Mohan worked very hard for Jubial engagement. And Harris is the technician first from the science faculty to get the patent, national patent. So this happened in my time. So why I'm telling you, he's a technician, of course. So those who brought a lot of development to the world, even the PCR, just before the corona. Corona came in 2019, PCR came in 2005. That technique, that developed a scientist from a company, not from even university. So if that not there, then we would have been struggling. So that's a sense of contribution. So ladies and gentlemen, I go into the touch of philosophy because this knowledge center, University of Jaffna, came to existence 50 years ago. This is a blessing for this region. I know most of you have been miss so much of intellectual pursuance unless this university came to existence. So we are the human beings, we can be good at expressing gratitude, irrespective of the personalities. Of course, this credit goes to the personalities who have contributed. Irrespective of that, this came from public fund. Every month I disperse 330 million, even the salary alone. Bursar is here. Salary alone, not the recurrent expenditures, securities, manpower, internet, current. So the public putting in. So I am going to, in my twilight time, I am so happy because I see some people like our general chairs, both sides, the short people are there. Ravirajan and Noble and Vignaruban, Velayamurthy and Ramanan group and Isramohan group, Gajapadis and all these people, when they invited grant and developed laboratories. I know Dr. Vignaruban developed batteries and storage and transmission laboratory. I had the privilege of opening it, that's all. Then another man come from northern hemisphere. He was during the communal riots, he left the Moratoa University and settled in Norway. He brought in millions, 400 million in 2 stages, Velayadabulla Dayalan. Then out of his contribution with the Professor Ravirajan, now we have to recognize our dean as a fellow of Academy of Science. He's the first one from the faculty. Please. I see fellow of Academy of Science. Of course it will come. Others will follow it up. I think Nobel application is there. Vignaruban may do. So now it's happening. It's not happening earlier. So I always say the future generation is better than our generation. How the man from Tenmaraji coming, Sabeshan doing a spin-off company in the thing, Siddharthan coming from US Energy Department. Then he told me, my batchmate Ravi invited him to Montana to do a PhD. While he was going to a PhD, he never witnessed a conference in this part of the world. In '83, we have a communal riots and all sort of scenarios happen. So wonders happen. Life bring opportunity as do our desire for it. So what is the human desire? My master always asks me, Sri, what is your desire? What is our desire? Eating, sleeping, mating, defending. So the storage laboratory, then our desire, we put the laboratory for nanotechnology, and then the chemistry, we had ahead plan 40 million with the Vignaruban, they put another laboratory, then IoT laboratory with the Ramanan group, and then best of best laboratories in the entomology, molecular biology. This is happening. Now even the people came for quality assurance are wondering. They say best laboratory facilities in this part of the world. Who created this? Our forthcoming generations, the latest generation, they still have another 15 years to go. I know wonders going to happen. I know some, at least we witness and chair them. Even Jayasuriya, when he took up managership for cricket team, he said, no problem. Our players will do. Our players will do. Please, public, come and cheer them. Fill the stadium and clap for them. That's what we had to do. We had to recognize the research contribution, being a come. So my master used to ask me, what is a desire? So then we struggle, not eating, mating and all this. Desire to know. Who am I? It's a question from ancient time. Our medical professor is here. So community medicine is there. We want to know our problems. The big data business is now there. Information highway is open. So we have opened first time in the Asia a center for, we have to get it from the generated money. I tell faculty of arts, humanities, now STEM to STEAM they say. Humanities is important everywhere. Even Sriharan says, medical faculty bring humanities. Now the doctor's problem, you know, entire country. Somebody opened up. Somebody talking about it. So humanities, ethics. So humanities, I tell you, for him, intake is 500 internal. Yesterday, I checked the list for yesterday. He died in the Punagiri in the heart attack by bicycling from agriculture faculty to Jaffna. Professor Kandaya. His son was witnessing the proceeding. A Japanese scientist is delivering the lectures. 2 billion grant we are managing in the JICA. 4 Japanese are permanently there to induct us. So wonders are happening in all faculties. So in the Knowledge Center, we have a good track record of all the Jaffna people. Even Nanda says, as long as they come to US, with no time they catch. Because the background education is there. Then, you know, our desire to know is mainly without creating knowledge, nothing could be known. So this center creating knowledge, now we are embarking. Earlier we just wrote papers. Now the diversified level, people are engaging. Even the UBL setup, we are thinking about commercialization. So that kind of endeavor, spin-off scientist has come. Submission, I know he will deliver something on that respect. So research is something our innate desire. Everyone wants to discover, at least discover something. I know everyone comment in the social media, they discover something or they see something. Our laboratory, Vidyanandan library, is a storage of knowledge. Knowledge is a subtle thing. So the Lord Krishna says, little advancement of knowledge may save you from the greatest fear of your life. That is the corona vaccination microbiologists did. So greatest fear gone. Similarly, so many advancement. Today I am speaking live stream happening. I lived in Indiana Road in Edinburgh, where the James Clerk Maxwell born. Did he do his research with a research grant or multi-foreign country visit? He is the one unified all electrodynamics into one compartmentalized equations. And from there, the signal processing originated. The top nuclear reactor is providing the energy. The solar cell people in the border studies, I always listen to them. They say renewable energy. No, the real energy source is running out of the energy, half-time gone. So nuclear energy revolution came in the 60s with the Einstein E = mc squared. He drove everything from postulate. No single experiment Einstein did. From there, nuclear generation came. The fourth industrial revolution took place. But our nuclear reactor is a fusion reactor, yet to be found for the human beings. Human one or fission one. That is 4.5 billion years old. So one scientist said, Joseph Fourier transform is a very important thing in the engineering sector. Fourier transform. Joseph Fourier said, the nature is the fruitful source of discoveries. The research are done to discover, to know. So universities are created for that purpose. Every man here, from cleaning staff to technician to the lecturers to the students to everybody, at some stage, every stage you are contributing. The book, the earthworm contributing without having anybody notice, they actually condition the soil. Similarly, everyone here in the university contributing. So VCR is a concept of the juice. Juice only come, I finish it off. The coconut, you have a skull. the laminated part, that prevent anything coming from inside, outside, choking. I know a lot of now the polluted world, so the choking should be there. The choking should be prevented, laminated part. Then there's a floating part. We had to float. There are a lot of problems, economic crisis, that crisis, even Britain there, economic, Europe, fight, all over the place. We had to float in this place. So that is the coconut second part. Then the skull. Now IoT, sensors, data processing. The machine is there, one of the best machine. So that is with us, the skull. And then the kernel. Kernel is the thing everyone enjoy to the food. So all the science are done to support our existence, our physical existence, our intellectual existence, our social existence, our emotional existence, our universal existence. So science support, so conference pay the way. I finish it up. So the kernel, then the juice. Juice we created, I think we coined this word with the Ravi in the certain time. I know first juice done when the Futa was on striking, Angaran was doing the back and everything. Sometimes he think I forgot. No. This is a publicity chair. It was done even not even in the university, it's in the Tilco Hotel. The juice is the final thing. Surendra Kumar one day said, when the LTD was fighting, when they got injured, they find coconut juice that infused to the human being so that it's readily accepted. The human blood composition and the Tambali water compositions are same. Not to worry about the package. So that juice is a gift. Now, lot of things are happening. The grants are coming. Even last Senate, we had a grant for Surveys and Charles for getting ready with our Tamil language data set and GPT environment to be incorporated with the linguistic department. So the cross-cutting discipline works are going on. Anyway, thank you very much, ladies and gentlemen. Time is more important. Thank you very much, ladies and gentlemen.
Thank you very much, sir, for sharing your valuable thoughts. As we reach a significant moment in our conference, we gather to celebrate our collective achievements with the release of the VINGNANAM Research Conference Proceedings 2024. These proceedings encapsulate groundbreaking research and innovative ideas that will shape the future of various fields, emphasizing our commitment to a sustainable and resilient future. We extend our heartfelt gratitude to all the authors, reviewers, and editors who have dedicated their efforts to bringing these proceedings to reality. It is my honor to invite Dr. P.A. Amalraj, Chief Editor, VRC 2024, to come forward and officially launch the proceedings.
So to launch the VINGNANAM Research Conference proceedings, I would like to invite our Vice Chancellor, Professor S. Sri Satkunaraja, to receive the first copy of the And also, I would like to invite Dr. Sabesan Sidambaranathan and Dr. S. Shuthanandan, Dr. N. Nanda Nandakumar, Dr. S. Sivanandan, Dr. T. Udyashankar to receive the VINGNANAM Research Conference proceedings.
distinguished guests, the keynote speakers and invited speakers, dear colleagues and participants. Good morning to you all. It's a great pleasure for me to stand before you as the chief editor of this VINGNANAM Research Conference 2024. Today marks a significant milestone, not only because we are gathered here for this conference, but also it's coincide with our Golden Jubilee of both Faculty of Science and University of Jaffna. So over the past 50 years, our university has been a pillar of excellence in education and research. So that what we are seeing today, to culminate it over the period of time, that's the evidence we have seen today. As you can see from our invited speakers and keynote speakers, some of them are from our alumni, so they are doing really great in the research and also the innovators as well. So we are really proud to have them here as a keynote speakers and invited speakers. So as we come together under the theme of research innovation for and sustainable and resilient future, so I am reminded of critical role that the research plays a significant role in shaping our futures. So the VRC provides is a vital platform for the scholars, researchers, scientists, innovators to come from overseas around the globes to share their experiences, share their knowledge, to share their research, and also, so there's here the innovative ideas over here in this conference. So this will contribute more sustainable and resilient world. So in the proceeding what we release here, so you will find a rich of collection of abstracts, so including 2 keynote addresses, 3 invited addresses. So we also have 37 abstracts, which has been rigorously reviewed, and also, so we selected after double-blind review process. So this is the process what we have done here. So this is the process we have done. It's evident that this is the research we are going to, the abstract the people are going to present it here is the evidence for the high impactful and also high quality research that we are representing here today. So I would like to take these opportunities to extend my deepest gratitude to all those who made this possible. To our keynote speakers and invited speakers, your contributions are invaluable, and we are honored to have your insight enrich our conference. To all the authors submitted the abstract and who are going to present today, so thank you for sharing your work and also for your commitment to advance knowledge. Special thanks must go to the reviewers who dedicated their time and expertise to ensure that our proceedings reflect the highest academic standard. Your feedback and constructive critics were crucial in shaping our proceeding. So additionally, I would like to express my heartfelt appreciation to the organizing committee for their unwavering support. Finally, I want to acknowledge the National Science Foundation for their financial support, which has been instrumental in bringing this conference proceeding to the life. And to my fellow members of editorial committee. So your unwavering dedication and hard work have been truly inspiring. It has been a privilege to work alongside such a working committee. So I hope that this research summarized in this proceeding and the discussion fostered by this VRC conference will inspire further research, foster continued innovation, contributing to the sustainable and resilient future that we all aim to achieve. Thank you very much.
Thank you, Dr. Amal Raj, the Chief Editor of VINGNANAM Research Conference 2024, for your tireless work and support on the proceedings. Now it's time to keynote address. I kindly invite Professor K. Vignaruban, Professor in Physics, Department of Physics, Faculty of Science, University of Jaffna, to introduce our first keynote speaker.
Good morning, all of you. To start with the keynote speeches, the first keynote speech will be delivered by Dr. Suthanandan. He is currently working as a senior research scientist, Pacific Northwest National Laboratory, simply known as PNNL, in the United States, and also a joint professor, the research professor at the Department of Aerospace and Mechanical Engineering, University of Texas at El Paso in the United States. And his title will be the Precision Imaging and Irradiation, Advances in Helium Ion Microscopy for Scientific Research. A few words about Dr. Suthanandan. He graduated from our department, Department of Physics, in 1985 with a first class honors. And then worked here for a couple of years as a permanent lecturer in the Department of Physics. And then he moved to United States for his higher studies. And also he resigned the position here in the Department of Physics. And he did the MSc and PhD at the Montana State University in the United States. And then currently working in the National Lab, PNNL. It is one of the national labs administered by the US Department of Energy. And his current work mainly focuses on materials for batteries, energy storage, and also he's working novel materials for nuclear applications, high resolution imaging of nanomaterials, environmental monitoring, atmospheric aerosol analysis, ion beam material synthesis and modification, and ion exchange mechanisms in waste storage systems. And Dr. Suthanandan published more than 300 peer-reviewed index journal papers, and I am proud to say he is one of the highly cited alumni from the Faculty of Science during the past 50 years. His publications are cited more than 11,500 times. That's the highest publication, the highest citations among the alumni of the Faculty of Science. And he received numerous international awards, including Outstanding Mentor Award from the US Department of Energy's Office of Science, and the PNNL, the Pacific Northwest National Laboratory, Director's Award for Outstanding Contributions to Science and Engineering Education, and also several other national awards. And he contributed to more than 250 technical talks in international conferences, and more than 35 invited presentations in the fields of material synthesis, modification, and characterization. He has recently named as a fellow of the American Vacuum Society, simply known as AVS, and it is a high recognition in this field, and you can simply understand in the PNNL, there are only 5 AVS fellows. It is the national lab, one of the national lab in the US. There are only 5 AVS fellows at the PNNL. Without further ado, I call upon Dr. Suthanandan to deliver his keynote speech. Over to you, sir.
Thank you. Thank you, Vignaruban. Thanks a lot. First of all, I would like to thank the organizers to giving me this opportunity. This is really an honor to be here. As Vigna Ruben mentioned, this is where I started, my scientific journey. So I'm a little nervous, I gave several talks, but talking in front of all of my friends, colleagues, and, future scientists, I'm a little nervous, so excuse me. So before I start my talk, these are the three pillars in my startup, So actually I started my undergraduate in Peradeniya, where I met Nanda here. So during the communal riots, we were displaced. And my dad told me, you cannot go to Kandy. I am the only son, so you cannot go there. But when we talked to late Professor Gunaratnam and Professor Kumaravadivel, they open-handedly welcomed us to finish our degree where we started at Peradeniya. So without them, I wouldn't be here talking in front of you. Especially, the education that I got from these three pillars is outstanding. So when I went to US, it is very easy for me and all the people that went from here, whether it's a physics department or chemistry or biology, you name it, all of them did very well in their, coursework or the preliminary exam or comprehensive exam. What we lacked that time, I'm talking about 40 years ago, we didn't have any research experience like what you guys have right now. So I did only 3 months worth of research. That is the only research I know when I left to US, right? So we were really behind on that one. But in the courseworks and everything, we were much superior than Americans and British people and all the other European people. Excuse me. So what I'm trying to say is, the students listening to this talk and young faculties, please do some research, because that will really going to help you guys, when you go to the higher studies, it will really help. So even 1 year of research, I visited yesterday Professor Vigna Ruben's lab and Professor Ravi Rajan's lab. These were very nice labs, So we didn't have that opportunity. So you guys should take that one and please, do some research so it will, it's a good benefit for you guys. Okay. So first I will just show you guys where I am from. I am actually from Sri Lanka, Jaffna, but right now I am living in US. And in US there is several states, right? And then I am from the western state called Washington. And we are 200 miles east of Seattle, the small town called Richland, where actually the first uranium was enriched for the nuclear bomb that dropped in Hiroshima, Nagasaki. So our place, as Vice Chancellor said, the nuclear field actually started in my region or our region. So we have a lot of nuclear waste there. That's the reason they started the national lab in that region. So this is the picture of the national lab. So we are part of the Department of Energy National Lab System. So US government funded 12 national labs, each one, each one has a unique, unique features. So we are one of the national lab called Pacific Northwest National Lab. So you can see from this Department of Energy's National Lab System produced more than 100 Nobel laureates, okay? And they develop technologies that affect our everyday life. If someone might have gone to abroad, you might have seen when you go to the airport checking, there is a whole body scanner. That was developed in our lab, ENNL. The CD that you guys used so long time ago, now no one is using it, that also developed in one of our labs here. And then they are multi-purpose, multidisciplinary. There are all kind of weapon lab, basic research lab, and then application-oriented lab. So this is our lab. So it is established in 1965, and we have 4 focus areas. One is basically energy reliance and sustainability, like a grid storage, batteries for the materials for new batteries and things like that. And then environmental science and technology, and that is the division I am in. And then national security, that is very important. After the 9/11, US government is pouring a lot of money into that one. And then, of course, the fundamental research. And we have more than 6,000 scientists, and these are the key facilities. The very first one, Environmental Molecular Science Laboratory, is the one that I am working on it. Okay, so now I'm going to ask a quiz for you guys. How many of people you know about SEM, scanning electron microscope? Can you please raise your hand if you know? Only very few. So that is a microscope is currently used in any field. You take any field, materials, biology, environmental science, nuclear science, everything. Because as a phrase called, a picture is worth 1,000 words, right? So one picture can give you a good description of what is going on. So everyone wants to put one image of something in their publication, okay? So the SEM is very well known for last 30, 40 years. So why we had to develop this new microscope that I'm going to talk to you guys to overcome some of the difficulties that SEM has, okay? So especially when you do the SEM for the biological materials or low Z materials like polymer, semiconductors or biological or medical application, they consist of low Z elements like carbon, nitrogen, oxygen. So when the electron beam hit the sample surface, it will damage it. So you cannot image very nicely because you will lose resolution. So what is the resolution? It's the minimum distance or minimum feature that you can see it from this microscope, right? So the SEM cannot give resolution below 50 nanometer. So nanometer is 10 to the minus 9 meter. So people have, all the things are going smaller and smaller and smaller, starting from the computer chips to everything. And these nanomaterials, as Vice Chancellor said, it is important part, nanotechnology, okay? So the SEM cannot give you that resolution. So only thing that you have to do, you have to find a new way of doing the microscope or new way of innovating. Is ideal for this conference. You have to innovate new techniques to image the samples below 50 nanometers. And then the depth of field, I will talk about that later. And the beam damage, we have to reduce that beam damage also. Okay. So that is the reason we need to have a new imaging techniques to overcome these issues. So here I am going to talk about the microscope called helium ion microscope. So the helium ion microscope is exactly the SEM, the scanning electron microscope. In the SEM, they use electron beams, but in helium microscope, we use the helium ions, okay? So why we want to use the helium ions? If you studied physics, you will know that the diffraction limit, it's limited by the spot size, right? And that spot size is equal to the wavelength of the beam that you are impinging on it, over the lambda is the incident angle. So if you look at the wavelength versus the energy scale here, you can see electrons has almost 100 times more wavelength than the helium ions with the same energy. So if you plug into this equation, basically the spot size is limited. It's very negligible. So we don't have any diffraction limitation there. So that is the powerful of the helium microscope. So now you can ask me, how do you generate the helium ion? So what we have is, in the helium ion microscope, we call source. The source, we have a single crystal tungsten 111 tip, the tip made out of single crystal. The physics students studied solid state physics, you will know that. So what we do is, we do some process. So the single crystal means the atoms are arranged periodically, right? So when you do some certain process, you will evaporate some of the ions or atoms coming out of it. At the one point, you will end up the atom like a 3 triangle there. So imagine, those are 3 real atoms sitting there at the top of the tip. And then what we do, we pass the helium gas, and we apply high voltage, and we cool the sample so that when the helium goes through, it will slow down the energy and then get ionized. And then you put some other attracting voltage to attract the helium ion. So basically my beam is formed by one atom. So imagine. So what is the diameter of the atom? 0.25 nanometer. So that is my beam spot. So no microscope can give you that much of a beam spot. So that is the advantage of the helium microscope. So here is the image of the helium microscope. So the top part, the cylinder thing, that is the source part, and the middle part is the detector to measure the electrons coming from the sample. I will explain that later. So basically you have three beams coming through it. Then there is an aperture. So what we do, we rotate the sample, rotate the source to align one of the beam to pass through the aperture. So we get the real small beam. Okay? And then you have some focusing and deflection, and then it will hit the sample. So the cost of this instrument is more than 2 million. It's only 50 instruments are available because it is very expensive, very difficult to maintain, so the universities cannot sustain that. Only national labs and industries have this. Only one university has Caltech. They have a lot of money, they have it. But if you compare to the SEM, there are 50,000 SEMs are there, so you can see. Because SEM is easy to do, but the helium microscope is little difficult to use. Okay? Okay. So the helium microscope, there are 4 imaging modes, so I will go through one. So the red beam is the helium beam. When it hits the sample, what is going to happen? It is interact with the materials and then going to emit secondary electrons. Okay? So basically you get the secondary electrons, the distribution, that will give you the topography of that surface. The second one, the Rutherford's backscattering. Again, physics students might have studied that. When you bring the alpha particle, helium beam, hit the sample surface and it can backscatter, right? Then that backscattering yield is proportional to z squared, the mass of that atom. So heavier the mass, more the beam will come. So that is called backscattered ions mode. And then if the sample is thin enough, it can transmit through the material, and then if you put the detector underneath, you can get more information, kind of a transmission electron microscope. And then the last one, when the beam hit the sample, it is energetic particles, right? So it can interact with and then emit some of the other particles, like a secondary ions. So we will use that secondary ions to get some chemical information. Okay? So in this talk, I'm not going to give a story like the other presenters are going to show. Here what I'm going to show you is this high-end microscope. What are the things that you can do just to give you the flavor that, sometimes you need this kind of high-end microscope to get some useful information. That's what I'm going to show you guys today. So the application of helium microscope is several things. The first one is the nanoscale imaging. Most of my talk is going to be on that one. Then the site-specific radiation, if I have time, I will go through that. And then the nanomilling. So as I mentioned, the beam is 0.25 nanometer, so we can really mill some graphene and graphite. So those can be used for the single molecule. It's a hot field now, single molecule detection. So you can see this is a 20 nanometer hole in that graphite sheet. And then you can do the lithography for the semiconductors. Because of the small beam, you can really do some nice lithography with a nanometer scale resolution. And then again, you can do some nanoscale chemical information, because as I mentioned, that secondary ions coming out from that process, we can use some chemical information. And then if you combine this chemical information with the topography, you can get a 3D image of the material that we call the correlative microscopy. Okay. So there are several advantages using the helium microscope versus ACM. So these are shown here. I will go one by one. The first one, it has an ultra high resolution and then large depth of field. Okay? It's not working. Okay, it's okay. So if you look at the image, that first one, the gallium beam, electron beam, and the helium beam. So this is a computer simulation of when the beam hit the sample, how that beam is going to interact with the atoms surrounding that beam, right? Or passing through that material. So you can clearly see if you look at the helium microscope or the helium beam, when it hits the surface, it's very small because, as I mentioned, it's only 0.25 nanometer, right? So the interaction volume is very small. If you compare the same with the electron beam, you can see it is a little bit a bowl of thing, right? So you can ask me why that is important. It is important if you look at the picture on the right side. When the helium beam or the electron beam hit the sample, I mentioned it is going to generate secondary electrons, right? So when you get the secondary electrons where the beam hits, then what will happen if you have interaction volume is more, the electrons can backscatter or travel through it and can come out from where, away from the impact position. So that we call SE2. So SE1 will come where it hits, and then SE2 come where it comes from inside the sample. So if you look at the distribution of the secondary electrons coming there, you will see a spike and then you broader one. So that's the reason we get the little lower resolution. If you look at the helium microscope, you can clearly see it is very sharp. So only electrons are going to come, is only going to come from where the beam hits. So that's the reason we have a high resolution. The high depth of field, so if you look at, again, the helium microscope, you can see the helium beam. It is really going through the sample and then diverging deep into the sample. But if you look at the electron beam, it is like a ball kind of a distribution. So you will lose some of the depth of field because it is going to blur when you go deep into the sample. So my passion is photography, so I usually correlate this with the photography. The helium microscope is like you are doing the measurement or you are taking the photograph with f8 or f9, so everything will focus. But if you do the SEM, it is like you are using f2.8, which is only at the surface. Okay? So here is the image, direct comparison between the same samples, SEM versus helium microscope. You can clearly see the helium microscope is crispier image, and you can see deep into the sample. This is another example of some carbon material. If you look at the picture on the left side, SEM1, you see the good surface, but when you see inside, those are a little bit deep. It looks like a fuzzy image. But when you look at here, even in the deeper sample, it looks a little bit, sharper images. So that is the high depth of field. Okay? So second thing is the surface sensitivity, right? So if you look at the SEM sample, what I meant is the surface sensitivity is when the beam hit, how many secondary electrons are going to emit, right? So if one electron beam hit the sample or one electron hit the surface, it will emit maybe one secondary electrons. But in the helium microscope, if one helium ions hit the surface, it may generate 10 secondary electrons. So you get a larger yield, so you will get the surface features very clearly. So that's what is shown here. So you can see this is the same sample collected with SEM, the blurred image, but when you did with the helium microscope, you can clearly see there are more features visible in that one. Okay? The second one is when you do if you take a material, there are two variety of materials, conductive materials and non-conductive materials. If you are doing with the biologically sample or medical samples, they are always, insulating samples. So we have a problem we call charging. So what happened is when the beam hit the surface, or any beam, doesn't matter, it is an electron beam or the ion beam, both are generating secondary electrons. So what is happening when the electrons went out, the surface will left with the positive ions, right? So that positive ions will interfere with the electron beam coming again, right? So that is a problem there. So what we do here in the biological field, they coat the sample with some kind of a thin gold or thin carbon film. So that will take the charge away. So doing that, sometime what happens, you will lose some of the resolution. I will show you some images. So what we do in the helium microscope, because since we are bringing the helium ions, positive ions, what we can do, when the helium beam hit, then we can bring another electron beam with a lower energy to spray on the surface, and that electron beam will charge neutralize the positive charge buildup, so we can do the imaging without any coating. So I will show you an image also. example later on. So here is the coated sample, some of the bacteria. So this is the coated sample collected with a helium microscope, and this is the one without the coating. So you can clearly see the coating damage the surface structure. So the spikes that we are seeing, it is not visible in the coated sample. So definitely the coating is doing something, so we want to avoid that. So here is another example. So this is the one single cell organism called Ferrominifera. You can find it in the ocean beds. So these minerals contain a lot of information that people or scientists can use to study the carbon dating kind of a atmospheric timeline. So what they want to do is they want to study how the spikes of this feature, the creature, is evolving if you involve with some kind of interaction with the minerals or proteins. Right? So when they brought to us, so we put it in the microscope, we couldn't see anything, it's just black there. But when I put the beam, the electron beam, then you can see I can clearly image the sample without any problem. So now what I can do, I can go deep into this, I can zoom it in, get high resolution, and you can see they have a lot of different structures, and you can different facets, and they are interested in these facets, what kind of facet surface we are getting, what is their dimension. You can see the dimension is like 500 nanometers. So they are very, very small things. So this is one of the examples. The third example, or the third the advantage of helium microscope is the beam damage. So again, I told you in the beginning, if you have a low Z materials, when you put the electron beam, it is going to damage the sample. So in this one is one polymer film deposited on a silicon substrate. When you did with the SEM, scanning electron microscope, you didn't see any, you cannot find any images. But when you do the helium microscope, you can see it, because the damage happening is the two different depth scale. For the electron beam, the damage happened at the surface, and the helium beam, the damage happened deep into the sample. So the surface have a minimum damage. So that's the reason we were able to get good images. Okay, so now I am going to go through a little bit of examples to give you the powerfulness of this microscope. So the first one, study of the nanoparticle toxicity. I think most of the biological people know the nanoparticles have been used for drug delivery, so many things. But the scientist doesn't know what that nanoparticle is doing to the other cells and walls and things like that. So in this particular example, they expose some of the nanoparticle into rodent, and they want to study where this nanoparticle end up in the rodent kidney, right? So here is the kidney of the rodent exposed to nanoparticle. It's a high resolution image. Then we zoom it in, you see some of the nice features there. And then if you look at the image, center of the image, there is a small dot there, right? So if I zoom it in even further, you can see there is a small particle sitting there. The dimension is only 50 nanometer. It's very, very small. But the interesting thing is that pores that we are seeing it on the surface of the kidney. So this is the first time they were able to see this kind of a porosity, because the porosities are even smaller than 50 nanometers. Some of them are like 5 to 10 nanometers. So no way they can image these kind of things with a scanning electron microscope. So they were really excited to see this image, and then they try to understand what is this and then things like that. So another example, this is in our lab. So what happened here is, so they injected zinc oxide nanoparticle into the lungs, injected to the mouse, and then they want to study where these particles end up in lungs. So they gave the samples to us. First they gave it to the SEM people. They did the measurement. They couldn't find anything. Can you find any nanoparticle here? Nothing. So they brought it to us. We did the measurement. We couldn't find anything here, right? So we were wondering, so what happened here, right? They injected it, the particle should be there, but we are not seeing it. So what we did, remember I told you in my first few slides, I can use two different modes, the secondary electron mode, or I can use the backscattering mode. So the backscattering mode means it can go deeper, because the helium ions can go deeper, and then it can backscatter from, if you have a larger particle, it can backscatter, right? Because zinc is a heavier mass, so it can backscatter more, right? So we thought, okay, let's do with a backscattering image. And then when we do the backscattering image, you can see all the particles are there. So basically, what this tells us is that when they put it, it is not on the surface of the cell, they are really deep into the one. So they penetrated deep into the cell. And then here you can go, and then same thing in a higher magnification, you can see these are like 5-10 nanometer size of the nanoparticle. So the next example is the bacteria-cell interaction. So in this one, they want to study, the scientists want to study how these Pseudomonas bacteria and the epithelial cell interact to each other. So the motivation here is they want to understand what is the invasion process of these bacteria, how they are interacting between them and between the cells, right? So here is the image, the larger image. Again, look at the error, the scale bar is 50 nanometers, so they are very, very, very small. And then you can see there are some like a small spider web kind of a thing that connecting bacteria to bacteria. That's the way they were communicating to each other. So if you look at the high resolution images, it's 200 nanometer, you can see it is, this bacteria is attaching to that epithelial cell wall. And then even if you go to the even higher magnification, you can see the size of that small fiber is 12 nanometer. It's very, very, very tiny. So they were excited, and they were doing all kind of other measurements. So what I'm trying to say here is the helium microscope cannot give you the whole picture, but it can help you to understand some certain problems. Okay? So this is similar. I will skip that one. So this one is very interesting. This is one of my best work I did in my lab, my career. So what they did here is, as Chancellor said, we went to space actually. So what they did is, there is an asteroid was passing through by Earth. So scientists want to study all kind of things. What is the mineralogy of the asteroid, topography, structure, what kind of space weathering. Weathering means what kind of damage it happened, because this asteroid is traveling almost 4.6 billion years through the space, right? So some of the scientists, Japan scientists, smart enough to send a satellite to land on the asteroid, pick up that sample, and then brought it to Earth. And then they want to study all kind of these things that I mentioned here, right? Then you can see the timeline. It started 2023, and it ended up in 2010. So it's a long process. So the science article, one of the best journal, dedicated the whole volume for this work, because it is that unique work, okay? So here is the picture of that satellite land. Is not real, the satellite picture is real, but the other one is like a computer animation. Landed on the asteroid surface and then brought it back. So they brought the sample. Again, I told you these are oxide sample or minerals, right? So they are insulating. But these are very precise sample. They don't want to put any coating. If you put the coating, then we cannot do anything else with that one, because only thing you will have it is the coating carbon or gold. So they were thinking, okay, where can we image this asteroid particle without disturbing the surface? So they came to us. We said, no problem, we will do it. As I mentioned, we put the electron beam, charge neutralize it, and then image it, right? And here is the image of the whole big block of one of the small particle collected from that asteroid. So it is, you can see it is around like 50 micron of size. So the main research theme in this one is to find what kind of weathering is happening there, what kind of damage happened during these 4 billion years of transit through the space. So they find all kind of things. They find the splash melt features, so it's like a melted, so that means it went through very high temperature process, and then it formed some grains, and it also has some holes. So that means something went and hit the asteroid when they are traveling through the space. And then there are some nice features like a triangle kind of thing. And interestingly, they found small white particles sitting on that asteroid. So we were wondering what that particle was. So when they did some extra experiments, they found out that particle or that feature is actually a interplanetary dust particle. So that particle came from somewhere from the Earth, somewhere from the space, and then tagged along with that asteroid. So they were very excited about this one, and they published in some very high impact journal. So this is one of the advantage using the helium ion microscope. Okay, so I will skip this one. The third one, the other example I'm going to show, I think, how much time I have? 5 more minutes? Yeah, I will finish quickly. This is the aerosol collected in some of the city in India. Okay, so in our lab and most of the DOE lab, they are very concerned about this air pollution, right? So they want to study about this, aerosol particles collected at different atmospheric length scale, different places. So when usually we collect these aerosol particles, most of the time they contain some, minerals or some solid particles, The first time we saw some bacteria, you can see in the corner, those are bacteria. So some of the bacteria are also transporting through this air and then reaching to faraway places, right? So again, we did that one with a helium microscope. We were able to identify these small particles. And they also found some other kind of particles that has some, like a viscous ball, right? If you have a clay ball, and then if you throw on the wall, what will happen? It will stick, make a splash, and then it will stay like a ball there. That's what they are seeing it here. So these are some of the examples of the helium microscope. Okay, so I will skip this one. So the final section I'm going to talk about is the chemical analysis, right? So we saw beautiful images, right? But can we get some chemical information, as I mentioned in my asteroid sample? What is that white stuff made out of? Can we identify some of them, right? That's what this SIMS technique calls. It's called secondary ion mass spectrometry. So when the ion beam hit the sample, it is going to produce secondary electrons that we use to image. And they also produce some secondary ions, like positive and negative ions. So you monitor that secondary ion somehow, and those secondary ions will have information about the chemical or the molecular information, basically mass per the charge. Okay? So here is I will skip this one. So the resolution of my imaging is 0.25 nanometer, as I mentioned earlier. But the resolution of the chemical information is little larger, because I mentioned that the interaction volume is little bit more here, because in this case, we are using the neon beam, not the helium beam. So we are using the helium beam to image it, and then we are using the neon beam to emit this particle, because we need a little heavier ions to generate enough secondary ions to come out of it. So that's what we use the secondary, the neon beam. Doing that one, we have a little bit larger interaction volume. That volume is around 10 nanometer. So it's still good, okay? So here is the things, the helium microscope, the beam hit the sample, and then we have a special holder that comes into the microscope, and then we collect the secondary ions coming from that sample, and then we put it into the mass spectrometer, and then when you put it in the mass spectrometer, these are some of the images. You will get some mass spectrum like this, and then you identify one of this particular peak, and then you monitor that one, okay? So what is the advantage of using this chemical information? Because you can use the chemical information for a very small area. So here, if you look at the semiconductor industry, their dimension, the chip dimensions are going down and down and down, right? So here, they want to study 500 nanometer by 500 nanometer area, what is inside that area as a function of depth, right? So you monitor the secondary ions. So here is the stack of materials, and then you can see the copper is there. So the interesting thing is copper diffused into the sample, into the silicate, which they don't want to use it. They don't want to have it. This is another example of the depth profiling. Again, there are stacked aluminum and copper and silicon. Now you can see the aluminum has a bump at the copper interface, and that also no. So these kind of things we can do in a very small dimension. So this is another example of the nanoparticle. So they mix lithium titanate nanoparticle and barium nitrate nanoparticle, and they want to see where this nanoparticle end up chemically, right? So you can image it, and then when you study the different, when you monitor the different masses, you can see the boron nitrate is segregated differently than the lithium titanate. So this is the, how do I say, the roadmap for these characterization techniques in material science or any field, right? So some techniques have a very high resolution. Some technique has very high detection limit. Detection limit means what is the smallest amount we can get, part per million or part per billion. So if you can see, there are so many different techniques are available, but to have a very high resolution and high sensitivity, there is no techniques available right now. So the only technique that can give you that kind of information is this helium ion microscope with a mass spectrometry. So it's a very expensive instrument. Only 4 of them are available in the whole world, and the cost is like almost like $8 million. So here are some other examples of nanoparticles. Then you can see there are some of them are lithium and then tin, and then they superimpose on each other, and then you can see they are at different places. So the correlative microscope I was mentioning, you can combine the secondary electrons image obtained from the helium microscope and then the mass spectrometer, put it together, then you can get the overall picture. So what we claim is that you can get 10 nanometer resolution chemical information and 0.5 nanometer resolution image resolution. Okay. So I'm not going to go through this one. So what we can do, helium ion radiation, helium beam as a radiation source. You know, in the nuclear fission and fusion, the helium are generated during the transmutation reaction. If you studied the nuclear physics, you might have known that one. So they want to study this nuclear reaction, nuclear interaction, so how these nuclear materials, the next generation nuclear materials, influenced by this radiation. So they cannot put it into the reactor and then study the material. So they want to accelerate that process. So to do that, what they do, they use accelerators and the helium ion microscope to mimic that radiation effect. Okay? So traditionally what they are doing is they are doing the helium radiation using the MEV accelerator or implanters. So their beam size is like 1 millimeter. So if you studied material science, you will know if you take a metal, right, mainly the nuclear industries are interested in stainless steel, I mean engineered stainless steel, put it that way. So they have so many different features, like grain boundaries, like normal boundaries, like particles, so many different features are there. So when you do the actual radiation, what is going to happen, it is going to average everything, right? So we thought, okay, how can we decouple this, right? Because only thing here in this place, if the beam is very small, I can go and put the beam into the one oxide particle and study what is happening surrounding area. Similarly, I can put it in the triple boundary or grain boundary, and then I can study. So we have started to doing this recently, and we have some results. Here is the one nickel coating, then we implanted. You can see it is like a 500 nanometer. It's a very small area. So we implanted that one, and then did some post-annealing studies using different conditions. So if you take the nickel and expose to CO2, you didn't see that much. It just oxidized. But if you do the same experiment with the radiated nickel, you can see the radiation caused some damage along the grain boundaries, and then the oxygen diffused through the grain boundaries and went deep into the sample. But if you do the same thing with the CO2 and H2 exposure, basically it formed the carbon. So I don't want to go deep into that one, but what I'm trying to say here is it is a very unique capability that we can pinpoint and then radiate the sample at a particular spot. So at the end, so the helium microscope can provide high resolution, high depth of field, high contrast images, basically for uncoated biological and environmental sample, and it can also give some chemical information. So it is a very powerful microscope. Unfortunately, not many people have this, but I just want to show you what the innovation can do to get more information. And with that, I will thank you. Again, thanks for Professor Ravirajan to give me this opportunity. And if you have any questions, please feel free to ask me. That's a good question, sir. I don't know. See, in TEM, that is the one going very powerful nowadays, because they can, basically the resolution, even though theoretically we can say 0.25 nanometer, but the electronics are the problem, right? So nowadays the electronic side is improving much better. So they can have a very stable beam, and then they can focus it very nicely, with a precise voltages. So, and then in the TEM field, they are doing some aberration corrected one and all those kind of things. So. No, it will helpful for the radiation studies, but not the particle X-ray. Because yeah. So we are doing a lot of work on that one.
Thank you, Sudhana. We are very proud of you.
We are doing a lot of work on that one.
Baby, and now we have come up like this. That's what I told you. You have all climbed Everest. One of the top microscope
No, sir, we didn't climb Everest. We have a long way to go.
Sudha, one question.
Yes.
We use helium ions for treating cancers. So how far it can penetrate, into the cell?
So this one, the helium microscope, my energy is 40 keV, so it cannot penetrate deep. So it is in the surface region, right? So
it's more useful for the skin cancer.
Yes, right, yeah. But our interest is not in the radiation in cancer. We are interested in the radiation material.
Right? Yeah, sure.
We are doing the material research, right? So how the new materials can withstand the radiation.
Yeah, sure.
And then decouple the other features. That's our main aim.
Thanks. Yeah.
But there are some accelerators that can, that it can
Yeah.
go deeper and then damage.
Sure.
Yeah. Yeah. No, that is not the secondary electrons, right? So those are the photoelectrons. So they are coming directly from the orbitals, right? The XPS, it is directly coming from the orbital, right? When you fit the X-rays, it goes inside and then kick the electron out. So this is a secondary electron process. The energy is very small, maybe 1 or 2 eV.
But normally we call that as a secondary electrons.
No, we call photoelectrons. OJ electrons and photoelectrons are higher energy than the secondary electrons. The background of those two electrons that you mentioned are the secondary electron. So I am the XPS, my other part is XPS, that's my bread and butter, We gave, one thing before I forgot to mention, we organized Professor Ravirajan, Vigna Ruban and Dayal, and we organized one conference called TASME. So it is a conference, a hybrid conference, and this time we got, I think, 30 people participated from University of Jaffna and, from Peradeniya and other places. So please participate next year. It is free for you guys. You will have a better, exposure, and then you can present your work. So please try to send your abstract there. Thank you.
If you have any other questions, you can discuss with him during the lunch hour. Thank you very much, Dr. Suthanandan, for giving a very nice talk, and also traveling from Washington to Jaffna is more than 35 hours of air travel. And thank you very much. To appreciate his talk, we are going to
Thank you very much, sir. While you are enjoying your refreshment, we would like to move our next keynote speaker. So I cordially invite Professor A. Ramanan, Professor in Computer Science, Faculty of Science, University of Jaffna, to introduce our next keynote speaker. I'm sorry, Professor A. Shyamalan will introduce our second keynote speaker.
So, good morning to everyone. Let's move to the second keynote speech. It's my great pleasure to introduce Dr. Sabesan Sidambaranathan. Dr. Sabesan is a multi-award winning entrepreneur with over 15 years of experience in the IoT space. As the founder and the president of his Cambridge University spin-out company, Pervas ID, he pioneered the world's most accurate passive RFID technology. His innovative work has led to the creation of world's leading large range of products that are transforming industries, generating significant exports, and even saving lives. Dr. Sabesan's contributions have had both national and international impact. He is renowned for bridging the gap between the academia and business, combining intellectual excellence with his entrepreneurial skills to bring groundbreaking ideas to commercial reality. His expertise spans entrepreneurship, strategic business development, and innovation leadership. Among his many accolades, Dr. Sabesan was honored as an Officer of the Order of the British Empire in the King's 2024 New Year Honours. He received the Royal Academy of Engineers Silver Medal in 2021 for his outstanding contribution to UK engineering and was awarded the Queen's Award for Enterprise Innovation in 2021. So today, Dr. Sabesan will deliver his keynote address titled Passive IoT Powered by AI. So please join me welcoming Dr. Sabesan. Dr. Sabesan, the stage is over to you. Thank you.
Okay. Very good morning, ladies and gentlemen. It is my real honor to be here this morning and to talk about passive IoT, passive means battery-free IoT, Internet of Things, powered by AI. The next 10 to 20 years is going to be a different world. Whether we like it or not, the AI is going to change us. Like the social media obviously has changed over the last few years, the AI is going to take us in a completely different path. And we have to be smarter. And if we are not going to be smarter, the AI is going to make us as a donkey. So you got to be smarter. Our kids in school need to learn even more mathematics in the early stage so that they can be developing their analytical skill, logical thinking skill. And so in Cambridge University, we're trying to go to school and promote that sort of analytical mathematical skills to primary school kids. But today I'm not going to talk about that, but today I'm going to talk about how my journey, being a little kid in Jaffna, Sarjari Hindu and Jaffna Hindu School, going to Moratuwa for very briefly for 6 months, and landed in the UK, and eventually spent 17 years in Cambridge, still there. I remember when I was first landed in Cambridge University, I was a very nervous student, and I can tell you, Cambridge University have transformed me who I am today. And the skill I have learned, the public speaking skill I have learned, the communication I have learned, the innovation I have learned, the commercialization, the skill I have learned, and none of this has been possible if I wasn't actually entered into Cambridge University. I can tell you that. Thank you. Normally the hang on. That's okay, it's fine. It's fine. Okay, perfect. Great, so I do have two jobs in Cambridge. One job is to be a fellow at Cambridge University and teach students, and also in the interview panel for admitting students to engineering in Cambridge University. Equally, I'm also founder and president of a Cambridge University spin-out company called Pavey Society. And so today I'm going to talk about the journey I have been since being a student. So this is essentially taking an idea, taking a PhD research from your university lab into market. How do you transform the innovative research you do, part of your research or PhD students or whatever the research you do, taking that idea from lab to market? So the way we've been taught in Cambridge is the number one key important thing is to truly define the market problem, the market gap, the market challenge you're trying to solve. Because often university researchers trying to invent and then solution looking for problem. The solution looking for problem is not the right approach. The problem looking for solution is the right commercial approach. The university have to adapt into that in the culture of problem looking for solution. So the first thing when I landed as a PhD student at Cambridge, I've been given this challenge. This is not an easy challenge. I'll quickly run through very briefly, is that the challenge I was trying to solve in retail, if I take the retail market, in retail, people steal items. When you go shopping, especially when the economy is low, especially when your income is low, you're trying to steal when you do shopping. And according to the US report, is that the shrinkage, theft, have increased to over 110 billion. 110 billion to retailers. That's a hell of a lot of money. And the modern way of shopping has also changed. Online, people these days order online, pick from stores, deliver to your home, etc., etc. If I now look at the aerospace, let's change this different sector. If I look at the aerospace, plane manufacturing is a complex process. Boeing, Airbus, Lockheed Martin. And when they manufacture a plane, they use a large number of tools to manufacture these planes. And also to maintain and repair these planes. And often what happens is that sometimes tools left behind the plane. Sometimes the tools are inside the engine. Sometimes the tools are inside the wing. And if the tools are left behind the plane, which is the FOD, prone object debris, it could be a massive safety risk. It could even bring the plane down. people on board could even die. But according to US, this causes $13 billion to this aviation industry annually. If I now look at airports, people travel around the world, right? And often luggage get lost or luggage misrouted or delayed. As a passenger, you have the right to claim compensation. Again, airlines have to pay out 400 million pounds annually to these passengers, 400 million pounds. Think about these numbers. These are not a small little Sri Lankan rupees or monies, right? These are a lot of money we're talking about. And then let's take one more sector, for example, healthcare, hospitals. Being able to track medical devices, we could say billions of pounds globally. Not to just the UK hospital, in the UK we call NHS hospital, but globally we can say billions of pounds. Not only we can say billions of pounds, but also we could save people's life. In fact, during COVID-19, if every country had the tracking system in place, we could have saved a lot of lives, a lot of loved ones. So if there's another pandemic, which I'm sure will be, in 20, 30, 50 years down the line, who knows, right? And if there's another pandemic, hope we can do better than what we have done in our healthcare service, in healthcare sectors. So once you define the problem, the next thing is truly understand the state of art. And that's the next important thing. This is how I've been taught in Cambridge University. So you got to really understand the state of art. What other people before you have trying to solve this? Because I'm sure there has been researchers around the world trying to look at the same problem and have tried to solve it. And there was always a solution they have tried. And so you got to truly understand the state of art. The more you understand, the better chance you're going to come up with a better way to solve it. And so when I was a student, I asked myself, how do we really solve it? The way to solve it is real-time tracking. If we can track every single luggage, if we can track every single tools, if we can track every single medical devices, we could solve all these problems in real time. So the conventional way has been done using barcode. And barcode been around for 70 odd years. But the challenge with the barcode, because it requires manual scanning, you had to scan one by one. You can never have real-time tracking. But advanced way of doing so-called RFID stand for radio frequency identification. And there are two types of radio frequency identifications. One called passive, which means batteryless, there's no battery whatsoever. The other one called active, which means it's battery powered. Like your mobile phone or like your AirTag. These are all battery powered devices. Nothing works without battery, right? Nothing works without electrical power, which is why you charge your mobile phone almost every other day. And so the active is absolutely fine. It has a battery, so it would work for a long time, for 3 to 5 years. But the challenge with the active technology is far too expensive. Typically, AirTag, if you buy from Apple, it costs you $30, $40 per tag. But the mobile phones are far too expensive to even put it on luggage. The passive, on the other hand, as I said, doesn't have a battery. And so you had to wirelessly give electrical power. As the Vice Chancellor mentioned earlier, Maxwell actually come up with all of these in Cambridge. You had to use the electromagnetic signals. You had to use the electromagnetic signals, transmit in the air. It's the same signals you get when you talk over the phone, by the way. And you use these electromagnetic signals and convert them into electrical power. And using that electricity, we can power these battery-free tags. We can power these electromagnetic little tiny chip. But the challenge with this technology is that because you had to wirelessly give electrical power, because you had to wirelessly give electrical current, the distance in which you can do that is well limited. Conventionally, you can only do within a sort of 1 to 2 meter. So it had to be a short range. And even then, it is impossible to achieve near 100% tracking because you're going to have a lot of challenges within that space. So my PhD was to, can I truly solve this passive RFID technology, this battery-free RF technology, and turn that into an active performing technology? Can I achieve the active performance using passive RFID? I know the challenge wasn't easy, but I took on, being a young early 20 man or 20 boy, I took on the challenge and said, look, let's give it a try. And I'm pleased to say, in my first year of my PhD, managed to invent a new way of addressing the physics to truly solve it. Because in Cambridge, you have 96 Nobel Prize winners. You would have walked on the same street as Sir Isaac Newton walked on. You will have seen Charles Darwin. You would have met Stephen Hawking. And when you have these sort of people, you would have sit next to the Nobel Prize winners. You would have had lunch with some of those former prime ministers. And when you have that sort of atmosphere, inspiring places, when you have that burning passion, you won't even sleep sometime. And I remember days I would have stuck in the lab for 2 days, 48 hours, no sleep, simply because I wanted to really solve this. And when you have that burning fire, burning passion, everything is possible. And so, and thanks to that, Cambridge University managed to solve that. And so today we have truly achieved world-leading innovation. Let me tell you a simple, this is the 300 page of my PhD thesis and 100 page of my patent 15 years ago. But let me tell you a very simple piece of work from that large 300 page of patents, 300 page of thesis. The number one basic thing, I do have 5 patents, and this is the first fundamental patent. And let me tell you the basic of that. Now, the basic thing we needed to solve is to truly achieve longer distance range with the near 100% accuracy. Because if you cannot detect these tags in every location, you cannot use for any tracking I mentioned, right? Whether tracking medical devices or tracking luggage or whatever that is. So as I said again, it's all about truly understanding the challenge from a state-of-art point of view. What other people have trying to do? Why they haven't managed to solve it? And in fact, once Albert Einstein said, it's not about looking for a solution. What did he say? It's not about looking for a solution. It's about asking the right question to solve the problem. So if you do ask the right question, you're going to solve it. So the challenge we had with the conventional system is that because these electromagnetic signals, when we speak on the phone, same electromagnetic signals, it travels in infinity number of directions. When I'm on the phone, it travels from the mobile phone to the other location in infinity number of directions. And often what happens is that the direct path signal get cancelled out with the reflection coming from the ceiling, from the floor, from the pillar, and all sort of places. And we call that in our technical term, so-called multipath fading. So imagine the direct path signal give you 1, the reflection give you -1, the 1 - 1 we all know is give you 0 sum, and that is what we call blind spot, dead spot. And in fact, most of you would have come up with a bad reception in your mobile phone, where within buildings you would have seen sometimes your bar is very, very weak, right? The same problem goes in the case of mobile communication. As a human being, when we are in the bad reception, what do? We move away from the bad reception to get a better coverage. But in case of luggage tracking, in case of medical device in a hospital, in case of tools in an airplane, they don't have legs, right? They're not going to move around. They're going to be sitting in the same place. So that's not going to solve it. And the people before me, there has been many researchers have tried to solve this before me. So it wasn't me trying to solve this before, for this same challenge. And I asked the question, how do they manage to solve it, and what approach they have tried? And the approach they have tried is that they thought the blind spot, you see the field hitting on the ground in some of the range location. Those researchers, people before me, thought they can completely get rid of the blind spot. They thought they can completely remove the dead spot. And I recognize the fact that even the God, even the Jesus Christ or Shiva or Allah, or whoever you call it, whoever you pray, even the God cannot completely remove the blind spot, because we live in a real world. There are going to be always reflection. There are always going to be reflection. There are going to be signal cancelling out. So no one can completely remove the blind spot. And so once you recognize that, you then trying to ask yourself, can you solve it in a different way? So I asked a simple question. Instead of trying to remove the dead spot, which is what every other researchers have tried to do in the past, what if I can move them around? I acknowledge the fact we have to live with the dead spot. We live in a real world, right? We don't live in the moon. We live in a real world in the earth. And therefore the dead spot always going to be there. Signals always going to travel in multiple directions. There are going to be cancellation. And so instead of trying to remove the blind spot, what if I can move them around? And that is a simple question I asked myself in my first year of my PhD. And how do we do that? is my the rest of the research to make that happen, right? Often groundbreaking innovations are very simple, by the way. Often the groundbreaking innovations are very simple. And so, in my 3 years of my PhD, what I have invented a way in which we can move this blindfold around. So imagine a tag, imagine a passive tag. By the way, the passive tags look like this, little sticker like this, or it can be a very tiny chip. This is what we put in a hospital medical devices. This is actually UK Hyson St. Thomas Hospital currently using it. And so if a tag, let's say is right here, if a tag at a blind spot, I will be able to move that blind spot to a different location. Suddenly that blind spot become a very strong hot spot, and therefore we can detect the tag. And that's what that dotted line trying to show you. So you can see that is a blind spot, right? Tag at a blind spot. If I can move that blind spot to a different location, that spot become a strong hot spot. Right? Suddenly be able to detect the tag. So by moving this blind spot really, really fast, we shall able to achieve detection in every location. So by inventing that, I have created a world-leading, that's only part of the invention, world-leading RFID technology to truly achieve 99+% detection accuracy. There is, by the way, there's always competition. So you compare yourself to the rest of the world. And the first thing you got to do, you got to create a unique selling point comparison, USP we call it, unique selling point. And so what is your unique selling point of your invention of your product? And so what I invented, as I said, a new way of addressing the physics to remove the dead spot. So today we are able to achieve 99+% accuracy, and compared to industry standard is 90%. Even the medicine only 99% accurate, by the way. If you look at the medicine label, it will tell you. Nothing is 100%, by the way. And if someone telling you 100%, they're clearly lying to you. And using advanced signal processing technique, be able to increase the range up to 20 meters or 240 square meters. So I could even cover this entire room with a single reader. And so I can even track every single attendee is here one day. Hopefully our Honorable Vice Chancellor will let me to do that, and we can then even see how many of you are seriously listening to the talk. And finally, also use machine learning, artificial intelligence techniques to locate each and every tag, locate each and every medical devices, to locate each and every passengers within 2-meter radius. Within 2-meter radius, almost like a GPS system within buildings. And not only produce that performance, but also at the lowest cost possible. Because often you could invent an amazing solution, but the cost of the solution is too expensive. No one's going to buy it. The return on investment is the key. And so we are able to invent all of it and sell it to the market, sell it to the world at the lowest, at the reasonable price possible. And therefore, return on investment is less than 12 months. Oh, thank you. Yes. So once you have a new innovation, the next important thing is to see, does this innovation or idea truly have a real addressable market? And often, investors want to see the addressable market is at least $1 billion. Not in billion Sri Lankan rupees, $1 billion. I'm talking about building a big business, right? I'm not talking about building a little small shop in Sri Lanka. I'm talking about a global business you want to build. And that's what you want to build too. And if we can't build few apples in Sri Lanka, we have solved the Sri Lankan economy problem, by the way. Not even few, just one apple. If we can't build one Apple company or one Microsoft or one Google, you have solved Sri Lankan economy problem. And that's what we need. We got amazing university here, Jaffna University, Vavuniya University, Eastern University. A lot of researchers are here with the top talented people, right? We just need to build that entrepreneurship culture and the mindset, and I'm sure you're going to be the tomorrow Steve Jobs. You're going to be the tomorrow Bill Gates, right? So when I was a little student, I've used my business school in Cambridge University to do this work. The MBA students, we often work with the management department or the business school because the MBA students are clever students, right? They know what they're doing. And so work out the market, and in my case, it was over $1 billion. So next thing you need is investors. A one-man band won't go long. Being alone, being just on yourself, doing amazing work, it's not going to go too far. You need a team of people. You not need a normal team of people. You need a star-performing team. The hardest things all is easier to invent. And if you have a groundbreaking, unique selling point ideas, easier to get money. I'm sure a lot of investors want to throw their money at you. But it's hardest to find a star-performing team. People ask the hardest thing. And so, in my case, I've done over the last 2016. So over the last 8 years, I've took $10 million investment, $10 million investment. Every 2 years going to market. Every 2 years you stand in front of a very smart investors and do elevator pitch. And this elevator pitch could be sometime 5 minutes. You got to convey your message within 5 minutes. You haven't got 2 hours to talk about your invents and your team and your ideas and your business model and exit strategy. All of these you learn. You can learn all of these skills, by the way. When I was a student here, I didn't know anything, right? All of these skills you can learn. And I went to Harvard University to attend a 1-week course called Authentic Leadership. And that authentic leadership course truly transformed me to be an authentic leader. Because each one of us is going to be an authentic leader. Regardless of whether you are the boss of this university or the professor of the university or the researcher of the university, you got to have the leadership skill. And so when I learned the authentic leadership course from the Harvard University, from one of the professors who was the former CEO of a $1 billion business, who has his own theory, what an amazing lesson they teach. And that truly helped me to become a true authentic leader. And so I took investment, 10 million, from some of these names you might recognize. Of course, Cambridge University is my first investor because, by the way, taking investment is almost like getting married. So when you get married, you don't just randomly go and marry a person. I know that's the traditional way of doing in northern east, but actually the better way to do it, you got to know the person. You do a bit of a dating, right? Understand you both have a similar characters at least, right? And then you want to get married. So similarly, we'll have we call speed dating with the investors, speed dating. Get to know each other, right? Does the founders get along with the investors? Because if they don't get along, they're going to break. It's not going to make the business, it's going to break the business. That's what happened to Steve Jobs. When he took the wrong investors in Apple, Steve Jobs was fired from Apple. And that was the toughest lesson he learned along the way. And so you got to get the right investors. So I took Cambridge University as my friendly investor. Of course, they would love to help. So that's where I invented, right? If the business is successful, they also take some percentage of that. Stanley Ventures is the venture arm of Stanley Black & Decker. Stanley Black & Decker is one of the $40 billion business in the US, the leaders in aerospace, and they have customers like Boeing, Airbus, and Lockheed Martin. So with these people, I took 10 million investment. So once you got the money, the next thing you got to do, you got to build a star-performing team. Now, when we build a star-performing team, again, I made mistake in early days, hiring some of the wrong people. Because I thought people with the talent will work together in the right team to produce the results. But later I realized it's not only the talent, but also their characters. So today, we equally weight not only your talent, but your true characters. Are you honest? You always been honest? Or you've been, really, we have a chemistry with you? Or open, or can we trust you? Because if you have a one poison pill in the team, it could kill the team. And so the characters is what we bathe more than the skill, because we tell the people we can teach you the skill, but we cannot teach you the characters. But I learned that again hard way. Hired some of the bad apples, right? We say the bad apples because they are with the bad characters in the UK. And so I hired some bad apples, but fired them over time. It's not easy to hire and fire, by the way. Difficult conversation you have to have, right, when you want to fire someone. Especially the salespeople. the people you hire to sell your product, they are very good at selling themselves. They're very good at selling themselves. So it's very difficult to see, are they true salespeople or do they really selling themselves? So anyway, learn the lessons and so build the star performing team. And that's the team I built is what produce, using the core IP, produce a series of product. You got to launch a series of solid product, which is what the middle line says, which is what I launch. And then you go after the customers and deploy worldwide. So I focus on 3 sectors. And it is important to, when you have a business, when you have your market, you got to focus on primary market sector. We call it low-hanging fruits. Because in any new technology, the key is to find the early adapters. Key is to find the early adapters. Because the new technology never tested, and therefore it's unproven. There's no customers before. And therefore, you got to have a referenceable customer who is happy to take the risk and give you £1 million worth of order. You don't want a little small customer, right? Because you are building a unicorn. You're building a $1 billion business. Unicorn means $1 billion business. You're building a unicorn. That is the dream of every founder. So we focus on 3 sectors, retail and healthcare and industrial sectors. In retail, today we're deploying with the 2nd largest retailer in the world, globally. And in that case, we putting our system up in the ceiling, as you can see, and it's tracking every single garment. The kids wear, the women's wear, the men's wear, every single garment the retail has. And the way it gets used, so throughout the entire retail shop, it gets tracked, right? If you go to the shop and if you pick an item, you go to the fitting room, we are tracking you. And if you're trying to steal, we can see Sabisan have stolen that item because it's tracking in real time, right? So you can also understand the customer browsing habit. What item you're trying, but not buying from the retail shop. So the way it using artificial intelligence, because we are keep on getting the data, using machine learning and artificial intelligence algorithms, what we do is, you can see, if you're looking for that polo neck top, it tells you precisely in the store on the map on the right-hand side, dot on the map, as you can see, it tells you precisely there in that store. It's almost like a GPS inside your buildings. So you can go and locate it. This is the future of retail. Whether we like it or not, this is the future of retail. With that tracking powered by AI, we're going to change the retail world. Thank you. So if I now look at aerospace, I mentioned about tool tracking, right? So that we can save $13 billion to aviation industry. With Stanley Black & Decker, who by the way also invested in Pavesadi in the business, we track every single tools, even a little small tools, as you can see. Even the small sockets. Even this tiny socket has little tiny chip. So we can ensure that no tools left behind the plane, and this get deployed worldwide with Boeing, Airbus, Lockheed Martin. These are the largest plane manufacturers. We also rolling out with the Delta Airline. Delta Airline is the 2nd largest airline in the world. These are not a small airline like Sri Lankan Airline. These are largest ones, right? So, and you want your reference customer to be big branded customer so that the follow-on customer will trust you, right? If your first customer, little small customer, it's going to be a long road. So we're tracking today the luggage in airports with Delta worldwide. And so the UL luggage won't get lost or misrouted or delayed. And then the final sector is healthcare. This is the one close to my heart because here we're truly saving people's life. So in this example, we're tracking medical devices. And so we can ensure the critical medical devices at the right place at the right time. So the patient treatment can carry on. In fact, because of COVID-19, there's still been very backlog in every countries. And delaying the patient treatment could potentially reduce your lifetime. You could even die, right? You only have one life, right? So you want to save people's lives. So that's what we do. We also track surgical instrument, as you can see on these slides, because in operating theaters, lots goes on. Not only sometimes mistake happen, right? No one is God, although we pray that doctors is a God, but unfortunately they are not. And sometimes they may make mistake, right? And sometimes things get left inside the stomach. And so by tracking that, hopefully we can reduce that. But also, decontamination process. Sometime what happened, the consultant used the tool on one operating patient, and not necessarily they have cleaned through the decontamination process before they use on another human body. And that's really bad. You're going to catch all sort of diseases. And so by tracking in real time, we can ensure that would never ever happen. So this surgical instrument tracking is the big thing we're trying to do in healthcare, so we can potentially save people's life. We're also tracking laundry items and cloth items and so on and so forth in the hospital. So it's been a tough journey, and I'm pleased to say the business is multi-million generating revenue business. And in Cambridge, we say 90% of the Cambridge University startup fails before they even get to 1 million revenue mark. The 1 million revenue mark is a good measure to say whether the business is going to carry on and scale, and the 90% of the Cambridge University startup fail. And Cambridge University startups often has a strong IP, strong USP. And one of the reasons it's fail is team, people. And the second hardest thing why the business fail is customers. You could have amazing innovation, you could have an amazing product, groundbreaking product, but if you cannot sell this product, if there's no customers going to pay for your product, no customers going to help you scale the business, if there's no revenue keep on coming, not many investors want to keep on funding you. Not many investors want to keep on investing in your business, and the business will eventually die. So the team and the customers are key. I'm sure you will all going to invent a lot more things, and I'll be delighted to help you with the invention. But the next important thing is to really hire the right staff performing team, and more importantly, then have the customers. So my final slide is what customers say. In the world, in entrepreneurship, we live in a philosophy that customer is always right. The customer is always right. And when you have that philosophy, customer is always right, you're not going to argue with the customer. You're not going to debate with the customer. You're going to educate the customer. When they don't know things, you will educate the customer. They will listen when you are in that expert. But you got to have that philosophy. And if you have that amazing customer, nothing can beat you. You can build a unicorn. You can turn the business into unicorn. So some of my customer feedbacks there. The first customer, Stanley Cripmaster, is the division of Stanley Black & Decker, the billion-dollar business I talked about. They publicly said, this is not just another overhead reader. This is the best and the only one able to meet the requirements of safety critical application, including FOD. So it's been a long journey, but and the business carries on. And I'm trying to promote entrepreneurship in Cambridge, and I love to promote entrepreneurship in Jaffna University. In fact, we started doing that. And so for the next few years to come, would really delighted to work with you to really help you promote entrepreneurship, promote innovation leadership, and hopefully you can also start business. So with that, thank you again for listening. Thank you very much. Thanks, everyone. Cheers.
Thank you very much, Dr. Sabesan, for very valuable, insightful talk. Do you have any questions? Maybe two quick questions. Any quick questions?
That's why even the big American firm ready to take the risk and go with the unknown Cambridge University little startup. So in our world, you had to have compliance in each and every country, because these are electromagnetic signal systems, right? In the US called FCC, you had to go through proper formal testing process. You pay a lot of money for that, by the way.
And there will be independent test cars will testing you to check everything electromagnetic field, expose it to patients, especially when you put in a hospital, you are exposing an electromagnetic signal to human head. So there's a regulation to ensure no human heads very close to those antennas, so very close to your mobile phone, for example. And so we've done all of those through that independent body, get those compliance, and that's how you get deployed worldwide.
So any other questions?
If you don't have question, I can ask you as well. I'm just kidding. Any other question, guys?
Okay, thank you very much.
Thank you.
So please accept our token of appreciation.
Now I would like to invite Professor T. Ishwar Morgan, Professor in Zoology, Department of Zoology, Faculty of Science, University of Jaffna, to introduce our invited speaker, Dr. Nanda Nandakumar.
So good morning, ladies and gentlemen. Thank you for your patience and continuously you have been listening the various talk. So I'm very proud to introduce Dr. Nanda Nandakumar, who is going to talk on the host microbial mutualism, paradigm shift in health and diseases. So if I recall his academic background, Mr. Nandakumar obtained his bachelor's degree with zoology major at the University of Pennsylvania. Then he moved to United States of America for his higher studies and completed his PhD program at University of Houston, one of the largest and old universities in Texas. So where he expertised on molecular and developmental gastroenterology. Immediately after his doctorate degree, he joined as assistant professor at Harvard's Medical School. So of course the Harvard Medical Schools in Boston is one of the oldest medical schools in the United States, founded in 1782. So there are 15 affiliated hospitals. So he joined in the general hospitals at the medical schools. So he has served there more than 2 decades as expert in pediatric gastroenterology. So pediatric gastroenterology, in the sense he was involved in the teaching and diagnosis, treatment, management of the gastrointestinal tract and the associated organs, glands like liver, pancreas. So working with internal environments, so anatomy is quite easy by going through the scanning, through the MRI scans, CT scans, ultrasound scan, or other image system, but you are going to listen with Dr. Sivanandan as well. But working with the cellular physiology internally, even in infant, is much difficult. So he worked for 2 decades. With his experience in the research career, he had been collaborated and interacted with many scientists worldwide, and he has published many science citation index articles, journal publication, more than 3,000 citations. After successful contribution in Harvard Medical School, so Dr. Nandakumar then joined as associate professor in biomedical sciences and pathobiology at Virginia Tech since 2012. Also, he actively contributed as research associate in pharmacology at Duke University in city of Blacksburg, North Carolina. With all his experiences, currently he established and serving as the Chief Scientific Officer at the A9 Health at Newton, Massachusetts since 2018. He has been started contributing his academic knowledge into the business, as well as he has been contributing as a consultant to the hospitals, including Jaffna teaching hospitals he used to visit, and he has been contributing his knowledge. I could see as the notable achievements, he extensively studied on the inflammation of immature neonatal gut and then necrotizing enterocolitis. So he has published some very reputed journals like Journal of Proceeding Natural Academic Science, USA, Journal of American Physiology. I could see until 2011, he had some very good publications. And he developed a number of novel mouse and human models for rare genetic diseases. Of course, it's a challenge for our countries like Sri Lanka, so creating such a models. But so well before 2010, he has created these models, and he has used for learning the cellular physiology. He further studied on glycosylation on the developing gut and its role in microbial epithelial crosstalk. Initial colonization at birth is followed by establishment of milk-specific suckling microbiota, followed by a succession to a dynamic adult microbiota after weaning. The underlying mechanism regulating the expression of these glycosylation enzymes and how glycosylations contribute to infections. And he has brought very novel models on behalf of that. So likewise, so he had many notable outstanding contributions. We are fortunate today, Dr. Nanda Nandakumar, with many scientific publications with more than so many citations. So all the way, he agreed to come and do this invited talk. So he came from USA, as Professor Vignaruban mentions, 24 hours on board, flying from USA to Sri Lanka, then 10 hours just for a 300 kilometers journey from Colombo to Jaffna. Thank you very much for your patience, sir, and your dedication. So this is over to you. Welcome.
Which one? This one second? Nanda symbol. So, okay. Yeah, we will change.
So, thank you so much. That's a lot. First of all, I want to thank all the organizers for inviting me. I have been coming to Jaffna for last 26 years every year to do various charity work. So, last time when I was here, when Professor Kumaravadivel was the dean, I asked him what I can do. He said, why don't you come and teach what you're teaching? So in 2006, I came and taught a course in cell and molecular biology. But what I want to tell all the young people who are sitting there, students and the young staff, all of you have a fantastic fundamental in biology. And you can, if you want, you can go anywhere and reach any height. Because I know, I was a school kid when this university was founded. I had a number of friends from the first, second, third year batch doing exceptional work in the UAS. And when they came, all of us were, we were like, as Suthanandan said, we literally knew nothing. But you had the fundamentals to succeed. If you are willing and willing to put hard work, you can go anywhere. After 24 years in Harvard Medical School, I started up a startup company because I realized that, there's more important things than, publishing papers. The second, I want to re-emphasize what Suthanandan said. Last 26 years, we have a meeting called TASME in Toronto, only for gathering all the Tamil Sri Lankan academics come together and talk about various things that we can do together. The last 3 or 4 years, we have about 250, 300 attendees, and now we are doing it virtually. So there are a number of students from Jaffna, East, Sabragamu, various people presented. And even if you are not presenting, join virtually, it's free. So join virtually and you can listen. When you listen, you'll understand. Students like you who graduated from here has gone and did exceptional in various fields. And if they can do it, I'm sure all of you can do it too. So I want you to remember that. So when I went to graduate school, the molecular biology was just coming up and coming, and as Suthanandan said, we have absolutely nothing about it. So we were willing to learn. We learned, and that transformation in the molecular biology has profound impact in all the health and all the biological science that you're doing. And now, in the last 10 years or so, another transformation is happening on either humans or any animals. Our genome is not the only one we control ourselves. What we are realizing is the microbiome we are occupying all our cells has a profound impact on what is the physiological state of you, whether you're going to be healthy, you're going to have a healthy life, healthy adulthood. Everything depends on the microbes you have and how they interact. That's what I'm going to describe it, because it is very important. In the Western countries right now, 1 in 10 develop inflammatory disease. And in about 50 years, almost all the kids who are born in Western countries are going to have develop inflammatory disease. So the understanding this is going to have a profound influence. So the greatest medical advancement of the 20th century is the introduction of antibiotics and vaccine. And because of that, right out of the World War II, there was a decline of all the infectious diseases. So that's a great prosperity, and because these diseases savaged human civilization for 60, 70,000 years. And at the time, around mid-70s, the lifespan of human is 45. Now in the Western countries, the lifespan is about 78. So that really has a profound impact. But everything has a cost. So consequently, when we were able to reduce it, consequently, we see an exponential increase in inflammatory diseases. And that has profound impact on everybody, for you, your children, and your grandchildren. Even though this is in the 90s and 2000s, is mostly in the Western countries, is beginning to seep onto the urban centers in the other part of the world. But I want you to focus on simple thing like between 60s and 70s, there was a period, there was no infectious disease and there was no inflammatory disease. There was a lag period before the inflammatory disease came, and always the question is why? And even in the Western countries, if the child is born in a farm, exposed to the elements of the farm, and if they are raised, they do not develop these diseases. The same parent, if they move to urban center, have a child, they will develop these centers. It is not genetic, it's a lifestyle. So the consequence of preventing or eliminating infectious disease really impaired our development of our immune system. Let me explain to you a little bit later, but you have to keep that in mind. This becomes going to be important. So the question is, why do we care? Why do you care? Because this is a problem of the Western world. More than 50% of all deaths worldwide attributed to the chronic inflammatory disease, including diabetes, cancer, cardiovascular disease, dementia, stroke. That you will recognize this is also a pretty big problem here. Not only in the Western countries, the urban centers of all these urban centers, all of a sudden developing disease like Western countries. Because the lifestyle we change in the urban centers are very much reflective of the Western lifestyle. And the question is why and how can we avoid getting these diseases? So Theodore Drevensky, a long time ago, in the 70s, said, nothing in biology makes sense except in the light of evolution. It is such a profound statement. He's considered the successor of Charles Darwin. So it really has, let me go through it and hopefully you'll come and begin to appreciate what I'm saying here. So this is the human evolution, right? So we started 1,000 years ago, left Africa and moved to various parts. We left Africa in 3 different migration. And somewhere between 13,000 years ago, we settled on various riverbanks and developed a civilization. Until then, we were hunter-gatherers. After that, our life is profoundly influenced by the agriculture and livestock that we live with. So during all this time, we have all these significant infectious diseases profoundly killed millions of people. So in the evolution, we have to develop mechanism. If we want to survive, we have to develop mechanism to prevent and outlast these diseases. So in the history of our life, we have acquired mutations and polymorphism in the DNA that really allowed us to withstand some of those infectious diseases and able to have a successful reproductive life. Success depends on you can successfully reproduce successfully children and they can reproduce further down the line. So coming back to the evolution in this 60, 70,000 years, ever since we settled down on the civilization, we selected genes and polymorphism that allowed us to withstand foodborne pathogens like salmonella, listeria, you name it, viral infection, cholera, whatnot. So we happen that. So this is, we can understand. The second part that really people do not appreciate is when we humans were infected by the pathogens and various molecules, even just goes out and walking in the soil with your bare leg, you are exposed to various microbes. All of us are evolved in the microbial world. So we have to always find a way to withstand microbes entering our cell. The way we do it is we develop immune memory, so that way we can fine-tune our immune memory so that we will not develop antibodies and protection against us, but against molecule. Okay? So what does this mean? First one, evolution selection. For example, in the European country, you see cystic fibrosis, but we don't see in this part of the world. Because when the cystic fibrosis evolved, it has a selective pressure against certain infection. Similarly, in our part of the world, for example, the thalassemia is pretty present, right? Because why it was selected and maintained in the population? Because it gives you a selective advantage over dengue infection, malaria infection. So that's how we select polymorphism and mutation and maintain in the population. So this allowed the enrichment of immune-related genes that are subject to natural selection and pathogen. So all of them, selection is based on pathogen burden, how and when we are going to infect it. And the question becomes, when we eliminate this pathogen, then what happens, right? So the second part that a lot of people don't appreciate is the accumulation of immune memory and fine-tuning of our immune memory. Because our immune system recognizes shape, 3-dimensional shape. So, for example, I'm just telling you that the last 30, 40 years, type 1 diabetes are exponentially increasing in the Western countries. And the reason, the antibody that, so the reason is we have antibody that attack beta cell that produce insulin. And they attack the antibody that attack the beta cell are targeted against that insulin receptor. And the epitope is that epitope, the host, in the bottom, AQQAP. And we have a microbe, if we are exposed to, that microbe also has the epitope of AQQGAP. If we are exposed to that microbe, our immune system will fine-tune our immune memory, negatively select all the things against self. We will not develop antibody against the beta cell. So we will not develop type 1 diabetes, only if you are exposed to that microbes. Okay? And this mechanism is called immune molecular mimicry, because a lot of 3-dimensional shape that microbes have, we have a very similar shape. So we have to have a very fine-tune our immune memory to make sure we are not selecting antibodies that attack ourselves. Because of this memory, we have all these diseases that are appearing very high rate in the Western countries. Some of them you will recognize: rheumatoid arthritis, type 1 diabetes, multiple sclerosis, various other things. This is just only the partial list. So coming back to this evolution, so what here happened is, until 100 years ago, we were subject to, exposed to these microbes, infection, pandemics, and everything. In the last 10 years, we just eliminated, right? By the vaccines and antibodies. By eliminating, what we have done is the fine-tuning of our immune memory, we have lost it. So the antibodies which sometimes recognize our cell, we are not eliminating. So that's lead to autoimmune diseases. In the US, 1 in 10 children are now born will develop one autoimmune disease. 1 in 10. In 50 years, all the children will develop autoimmune diseases. And this is strictly lifestyle, because genetically, our children in the, whether US or here, and your grandparents are not different. There is no natural selection happening within 2 or 3 generations. So the question becomes, how come when the grandfathers and their grandparents had same mutation, same polymorphism, they didn't develop diseases, whereas now children who are born with those same polymorphism, they are developing diseases. If all of you go and sequence your genome, you will be carrying multiple polymorphic mutant allele. You should develop multiple diseases, but you don't. And the question is why? So ultimately the question, the secret lies in the microbes that we have. So we are born in a microbial world. As soon as you are born, microbes colonize your cell, right? So whether your skin or lungs or gut, urinary tract, anything exposed to outside, microbe is colonized. So we have more microbes in our cell. Most of them are harmless. Some of them are very beneficial, okay? Out of this microbe, the microbe that colonizes our intestinal tract has so much of undigested nutrient. So microbes thrive in our gut. So that's the reason, just in the colon alone, we have something in the order of 10 to the power 14 bacteria. The more number of cells in a bacterial cells than our entire body. Okay? So until we started a agricultural civilization, our lifestyle is a hunter-gatherers. The microbiome of the hunter-gatherers are very different than the microbe of ever since us. So we were able to show that by we can go to the certain tribes in Africa who are still living as hunter-gatherers. And when we isolate the microbiome and sequence it, it was completely different. Whereas the rest of the world, we may have a different microbes in the South Asia, different microbe in the Western countries. The functionality of the microbe that colonize in every part of our body is almost identical irrespective of which part of the world you belong to. Okay? So most of the microbes are in the GI tract because that's where we take food. And most of the food we don't digest, right? Most of the fibers you eat cannot be digested by our digestive system. And they are digested by the microbes inside in the colon. And the bacteria, microbes digesting undigested food contribute to 1/3 of the energy you acquire. If we don't have the microbe, you have to eat 5 times the amount of the food, get the same nutritional calories. Not only energy, but also various vitamins, important molecules these microbes produce. So in essence, these microbes and us have a symbiotic relation, mutualistic relationship. We provide resident, they provide material that benefit for us. So that's the reason we survive. And also having the right microbes, even the pathogen comes, they will not attack us. So that's the reason if you have a healthy microbiome, even if you eat food contaminated with salmonella, you will not get infected. So as I said, this is number of genes in the genome, but we have so much more in the microbial genes in our gut. So what does that mean? What that means is we have various metabolic pathways that microbes can generate various molecules that we cannot generate. But we readily absorb them, use it to regulate our system, energy, various things. I'm going to go through that a little bit. So as I said, until you are born, you are sterile. So initial colonization happens just after birth. So it depends, so all our microbiome depends on number of these factors. The first microbiome you get inoculated is by your mother. If you have a normal delivery, the vaginal flora is the initial microbiome. By the way, vaginal flora has a more health-promoting bacteria in ourselves, okay? And if you are a preterm babies, the inoculum becomes a nurse's skin microbes. And then type of delivery, antibiotic use, early life antibiotics, formula feeding, exposure to a pet, all of them have impact on the microbes that initially colonize. So in the adult, we have something in the order. This is strictly in the colon, in the large intestine. We have in the order of 10 to the power 14 bacteria, 10 to the power 4 viruses, various different viruses, archaea, fungi, various eukaryotes like yeast, different type of yeast, and the phage. Those are viruses of the bacteria. All of them forms a cohesive, integrated ecosystem that live very harmoniously with ourselves. And having this complex bacteria is a reason we still carry mutation for diseases and we don't develop diseases. So the microbes that we have responsible for the digestion of carbohydrates, non-digestible carbohydrates, they provide energy, fermentation energy, organic acid, all the short-chain fatty acids we absorb in our body comes from the microbes. We have four transporters, 3 different binding protein, 4 different transcription vector activated by short-chain fatty acid that are produced by bacteria. So we evolve various systems expecting to take advantage of microbial metabolite for our healthy living. And most of the bacteria are anaerobic bacteria. So right now in your gut, the microbe that you have, they feed on endogenous carbohydrate, glycan, on the mucus and various molecules we produce, and the food that we eat. I'm sure a number of you may have, for example, Kandasasti, you would have fasting for 6 days, right? You'll be only drinking milk and the fruits. So at that time, these microbes only fermenting on the carbohydrate we produce by ourselves. So what that makes us interesting is that what type of food we eat, when we eat, make a profound influence of type of microbes that we're going to have. And that have a profound influence whether you're going to be healthy or you're going to develop diseases. So in the stomach, we only have 10 to the power 3 bacteria. I mean, just for a moment, think. The pH of the stomach is pH 1 or 2. Even at that pH, we have 10,000, 100,000 bacteria living there. So they can live in very extreme condition. And the duodenum, we have 10 to the 13, 14, and small, but the most important one in the colon. And the bacteria that we have, or microbiome, I mean, when I say bacteria, but it means fungus, everything that included. The microbiota that we have in the colon have profound, and these are the type of species we have. And if we get dysbiosis means get disrupted. When you take when they take antibiotics, we are messing up with the gut microbiome. When you have chemotherapy, that will get microbiome. You can do anything to your body. As an adult, you can do anything, antibiotic, chemotherapy, various treatment. Within 3 or 4 months, you will get back to the original microbiome you had. Whatever you have, you're stuck for the rest of your life. You cannot change it. You can give them few things and here and there, but basic microbiome will remain the same. After 3 years, whatever you have, you're going to have for the rest of your life. So if you disrupt this microbe and you really don't have a healthy microbiome, you have developed various brain disease, various endocrine disorders, various heart disease, lung disease, liver disease, pancreatic disease, bone disease, muscle, skin, reproductive, kidney, bladder. All the diseases are given there. And if you read those diseases, I'll guarantee you that you know somebody who had the disease. So this is called gut-brain axis, various gut axis, because the metabolite that we make in the microbes are absorbed and they go various part of the body and they have a profound influence of how each tissue function in homeostasis. So early time, ancient microbiota, we have much denser, different lifestyle, different gut microbes. By having a modern lifestyle, what we have converted in the complex, dense microbiota into the simple one. The simple example, ever since we have refrigeration, ever since we have commercialization, if you ask your parents or ask your grandparents, they would have food, unpolished food, right? Unpolished rice, unpolished grain. They'll be eating different season, different food. Different fruits, different time. You can't go to the supermarket and buy. They just have to, whatever locally manufactured, they eat. So what that is doing is every 3 months, every season, you are eating different food with the different fibers that really maintain certain sets of bacteria in your gut. But now, you go to the supermarket, buy the same banana. I'll guarantee you that in US, my children only had one banana. So they are exposed to the fibers on that banana. Whereas here you can have 10, 12, 15 varieties. And the fibers in each banana is different fibers. And that allows you to have certain different bacteria in yourself. Similarly, most of you love to eat white rice. But when you are polishing, you are removing all the fibers that really necessary for have a healthy microbiome. So that's the reason now people always talk about taking fiber, eating not brown rice, because this is the reason. So modern lifestyle, reduced gut microbe, due to diet, healthcare, sanitation, physical activity. And by sanitation means, I'm sure most of you use antiseptic wipes, right? So by doing so, what you're really doing is disrupting the microbe that you have in your skin. And that disruption is in part cause various eczemas and various skin diseases. And we never used it 50 years ago, right? So we were healthy too. So we don't have to use it. So we have to be careful what you think. So, yes. So effect of urbanization. So what really has happened in modern life, the increased consumption of refined sugars, antibiotics, chemical antimicrobial, exposed to air pollution, water chlorination, all of them have profound impact on the complexity and the diversity of the microbe that we have. And they have a profound influence on whether you're going to have a healthy lifestyle or not. So this is traditionally, if you ask a grandparent, this is the lifestyle. They have a very active lifestyle. They have a grain, fruits, various different things, but only very little meat on the top. If you are vegetarian, you are not even eating that. Most of us like in a sutta, so all of them are vegetarian. So this was the food that we ate, and the food also varies from season to season. So the type of fibers undigested food we're going to have is very different from 3 months to 3 months. And that really enriches the gut microbiome. And what we have done now is shifting diet, really from traditional food to the one with high sugar, fat, processed food, that really reduces the microbial complexity. And eating fat with less diverse carbohydrate, less fiber, really make it, the carbohydrate metabolism of the microbes are very simple now. And that's really not a good thing. With less physical activity, diabetes, obesity has risen, and there is a higher mortality due to increased cardiovascular diseases. So if you go to if I go to the hospital, I was there in the diabetic center, diabetes is the #1 killer in this country. And the South Asian, diabetes is more important for the cardiovascular disease than cholesterol. Having high sugar and metabolic imbalance has a profound influence in what type of disease you're going to get. So therefore, you have to learn how to eat unpolished traditional grains, which essentially provide various different type of fibers, and eating different type of fruits and everything so that you are always enriching. And this has to happen from the childhood, because as soon as the baby is weaned from mother's milk to solid food, they're developing the adult microbiome. So this is happening in the first year of life, right? By year 3 or 4 and 5, microbe is set. So you have to introduce this type of variation. I know I have children, I know it's a very hard thing to do, but that is very, very, very important. So I really want to let you know that traditionally, we ate this kind of grains. I'll guarantee you that most of you don't eat any of them anymore. Some of you. So, but the advantage is all these grains provide different type of fiber, and that fiber makes sure the microbiome is still enriched and diverse. In every disease that we talked about, we have developed protocols that we can change the microbiome from the healthy person to the diseased person. By just merely changing the microbiome, putting the healthy microbiome, we can eliminate this disease. I just give you a simple example. Obesity is a big problem in the US. So we were able to show in the animal model, if I give the microbiome of the healthy person, mouse model to the obese mouse, they won't be obese. Vice versa, if I give microbiome of the obese mice to the healthy mice, I can convert the healthy mice into obese mice. And we were able to show that in the human. We were able to put the gut replace the microbiome of the obese person with the healthy person's microbiome, and they're no longer obese. And the vice versa works. We can put the microbiome of the obese person into a healthy person. We can convert a healthy person into an obese person. So what that's telling us is having the right microbiome can override your genetic predisposition. So the important lesson is but the problem is, if you look at the healthy person everybody has a different microbiome. So right now the secret is we have no idea what is the magic formula is, because all of us are genetically different, right? So it's different. So because of this, we have increasing inflammatory disease, metabolic disorder, brain disorder, and in the last 100 years, what we were able to show, we had the data on the stomach microbiome, so we were able to show every generation, we were decreasing the complexity of the microbiome. When we go below a certain threshold, that's when all these development disease happens. You have time? Okay. So there was a section on, because a number of you may have children or grandchildren with autistic spectrum disorder. That has profound influence. The microbiome has a profound influence. Having the right microbiome, you will not develop these diseases. So just example, this is all these bacteria producing various vitamin B. All those vitamin B contribute to various neural transmitters, neural connection, neuronal effects. So they have a profound. So what we have to remember is what is the role of antibiotics and vaccine, how that helped us, but also how it's hurting us. Impaired immune memory, urbanization and modern lifestyle, how that is bad. Significance of microbiome during pregnancy, I didn't talk about it. As you are thinking of becoming pregnant, thinking about having a complex microbiome is really healthy. Factors affecting microbiome succession, so what really happened after birth. And the type of milk you give, mother's milk is the best one, not the formula, because mother's milk has fibers that is very unique. And the importance, the fiber-rich diet, and microwave produce short-chain fatty acid and metabolites. They are so profoundly important for the metabolic status of your body. And the role of neurotransmitters and onset of autism spectrum disorder that is contributed by the microbiome. and microbial vitamin B in CNS function, generational decline of microbial diversity. That is the reason in the Western countries we have seeing this increasing inflammatory disease, metabolic disorder, and neuronal disorders. Not only autism, even Parkinson, Alzheimer's, all those things. All of them are profoundly influenced by the microbes. And then second thing is with anything else, with the aging, we also lose the complexity of the microbiome. Not only the microbiome, but also immune competence. So thank you. The questions, I just want to leave with you this to tell you what the impact of microbiome on every system in our body. Thank you so much.
Thank you very much, Dr. Nanda Kumar, for your detailed talk. So on behalf of VRC Conference Committee, so we appreciate your talk. So let's please accept.
Thank you, sir. And I'm afraid that we are behind the schedule, so our upcoming speakers will cooperate with the time, and also, of course, audience. So it's my pleasure to welcome Professor Meena Senthil Nandanan, Professor, Department of Chemistry, Faculty of Science, University of Jaffna, to introduce our next invited speaker.
A very good afternoon to one and all. Thanks to the organizing committee of VRC 2024 for giving me this opportunity to introduce Professor Sarasananda Raja Sivanandan, a proud product of the Faculty of Science of University of Jaffna, and I am glad to stand before you today as one of his batchmates. Professor Sivanandan is a senior scientist at the Peter MacCallum Cancer Centre in Australia, one of the world's leading academic cancer centres dedicated to treatment, research, and education on cancer. He also holds adjunct associate professor positions with RMIT University in Australia and Bharathiar University in India. With over 20 years of experience, he has made significant contributions to the field of medical physics through his work at various renowned institutions worldwide. He earned his PhD in medical physics from the University of Canterbury in New Zealand, and his research led to 2 international patents that are currently being commercialized. Professor Sivanandan is a fellow of the Australasian College of Physical Scientists and Engineers in Medicine and holds a registration as a clinician scientist in medical physics in the United Kingdom. He has served as an international expert in medical physics at the International Atomic Energy Authority, leading educational projects in Asia, the Pacific, Europe, and the Middle East. Professor Sivanandan is an author or co-author of over 50 publications and has delivered invited talks at leading international conferences. He was a recipient of the highly competitive Australia's Endeavour Executive Award. Professor Sivanandan is a distinguished alumnus of the Faculty of Science, having graduated in 1993. During his undergraduate period, he was fondly remembered, as many of us, as Library Sivanandan, for his dedication to his studies and spending most of his spare time in the university library. From 1995 to 2006, he served as a lecturer in the nuclear medicine physics at the Faculty of Medicine, University of Jaffna. Thank you, Professor Sivanandan, for accepting our invitation and delivering the invited talk on optical fluorescence imaging characterization of tissues and cells using unsupervised machine learning techniques. I kindly invite you to the stage. Thank you.
So good morning to all of you. So today there are many talks on microbiology, bacteria, imaging, all sort of things. So I am also going to talk something related to that using the current, the supervised or unsupervised machine learning techniques. That's also the current trend in research. First of all, I would like to thank the organizing committee to invite me as an invited speaker here. And also, Vice Chancellor asked me why you didn't wear the coat. I said, physics people are different. So for Shuthanandan, for example, he didn't wear the tie. So I, so I didn't wear the coat. So all right. So today I'm going to talk about something very related to that that some others are talking this morning. This is actually done a few years ago as part of my research, but I choose in this topic because nowadays the interdisciplinary research and multidisciplinary research are the key focus. So here in this kind of work, you need a good collaboration between physicists, biologists, chemists, mathematicians, all sort of people. But as few speakers mentioned, the collaboration is the key for success, right? So, but that is lacking in many places. So how we can improve that, so all depend on a lot of skills that we have been developing throughout our career. So the interpersonal skills and so many, collaboration skills should be taught at the school level or even before. But that is lacking in many places. But unfortunately, or fortunately, we had to work with people with different backgrounds, different ethnicity, different cultures, right? So this is my experience from many places. So again, I am talking about bacteria, and people talk about bacteria, but I'm talking about bacterial spores. I think you all heard about it. It's a sleeping stage of bacteria. It can stay as a sleeping stage for millions of years. At the end of the 19th century, Kohn and some other scientists discovered these bacterial spores as part of the life microorganism. So endospores are produced as a survival mechanism of life, right? And it can respond to adverse conditions such as heat, radiation, chemicals, etc. So as I mentioned before, the spores can remain in a viable dormant state called sleeping state and can undergo no detectable mechanism. So you can't even see it or you can't even find it. So, but when the conditions are favorable, they can become a vegetative live bacteria. So spores contain almost no water, right? And it contains the genes of all the bacterium. So this is a typical spore structure. You can see a typical cell. So this is slightly different than the typical human cells. So it has a lot of compartments and layers. So why do we need bacterial spores characterization? As you all know, the biological terrorism is one. And also, as many people mentioned here, there are pathogenic bacteria that harm our health or do some bad things on human lives. So bacterial spores are hard to detect, but are still an important source of bacterial contamination. But the current systems for detecting is costly, time consuming, and even need trained people to handle it, because certain bacterial spores are pathogenic and it can cause problem to humans. So this makes it vital to develop and rapid specific methods for their characterization and identification. So as physicists and chemists, you all know luminescence spectroscopy, so I don't want to talk much on that. So because this spectroscopy, there are various kinds of spectroscopy. So I'm going to talk about fluorescence and phosphorescence here, but there are Raman spectroscopy and so and so. So you can apply these things in the real world by collaborating different departments and different subject areas. So fundamentally, fluorescence is the rapid process, right? It is the transition between singlet states in a molecule. And phosphorescence is a transition between the singlet state and the triplet state. And is a very rapid emission, it's highly sensitive technique, high cross-section, a small sample size is enough to detect a minute sample, and so. So this techniques is not only applicable to microorganisms, but is even living cells like cancer, detecting cancer, or characterization of so many diseases, or so many other microorganisms. Detect Alzheimer's disease of the brain, and characterization detection of microorganism, as I mentioned before. So the fluorescence is a very unique technique. I don't need to talk about this, the all fundamental. But what I wanted to show here, because these are very highly sensitive and easy to apply in a small set of laboratories, and do a lot of research based on the current machine learning and AI-based technology. So fluorescence, single emission spectrum and single excitation spectrum, and one of the keys, the fluorescent excitation emission matrix, is a 2 or 3-dimensional matrix to gather all the important information from the samples. Why fluorescence? As I mentioned, is a resonance process and a large cross-section, and is a highly sensitive technique, and is fast and has large number of parameters involved, so you can deal with it. So as I mentioned before, in a biological sample, there are various compartments and components, including chemical components. We have many chemical components in the microorganism and in living cells. So some of the notable ones are NADH, tryptophan, pyridine, tyrosine, and so and so. But in bacterial spores, there are some specific chemical component. That is a unique component in the spores that many people are trying to characterize or trying to use as a biomarker to detect bacterial spores. So many people try to develop the new way to detect bacterial spores. We try to do with the fluorescence with the DPA, the unique chemical biomarker within the bacterial spores, and did so many work on that. While we were working on that, as Dr. Sabesan mentioned, you have to be smart enough, to see things. Is any small things changes while you are doing some experiments? Can you do something based on that? So during that experiment, all of a sudden, the fluorescent intensity enhanced with subsequent measurement. Then I thought, why it's happening? Why is happening this, all of a sudden is increased with the one by one, repeating the experiments. Then I found is something happening, right? So then I exposed the spores with the ultraviolet radiation, right? And found that the fluorescent quantum efficiency increased about 30 times. It's a huge increase in fluorescence that actually lead us to develop a new detection technology based on that the unique biomarker. So I'm going to talk here more on machine learning because I don't want to talk about my invention because that is already been patented and anyone can look at on the website. But what I'm trying to focus here on the how we apply machine learning into this kind of experimental work. The main problem in spectroscopy is the overlap of signals and background noise and so many other irrelevant signal, for example, from Raman scattering or Rayleigh scattering, is part of the fluorescence spectrum. But those are unwanted signals. How we can remove them and how we can improve our signal to noise ratio in the imaging. So in those kind of problems, these machine learning's helping a lot. As you all know or heard about this principal component analysis, one of the very highly sophisticated analysis can be used in many applications in medicine, biology, all sort of chemistry, all sort of subjects. So PCA is a popular unsupervised machine learning technique for reducing the damage because we have plenty of data. It's a huge number of data. Can we use those data? We can't find any information from them. So our aim is to minimize or reduce the dimensionality of the huge number of data. So this PCA helped to reduce the dimensionality data while still maintaining the most of the useful information. So principal components are nothing. It's a kind of a correlation matrix. You all learn about eigenvalue, eigenvector problem. So it's actually decomposing the correlation matrix into eigenvectors and eigenvalues. So those eigenvectors with higher variance of eigenvalues represent the maximum variation in the data set. So those components are useful to get more information out of your larger number of data. So there are various ways to find out what are the important components to analyze the data set. So there are various criteria available. I don't want to talk more on the theoretical base on PCA, but I mainly focus on the application. So the most important components or the large weighting factor actually contain the real spectral signatures, features or feature extraction. So least important components with small eigenvalues or weighting factor represent noise or unwanted signals. So what are the advantage of PCA? One is a very all know that dimensionality reduction. The other one is a feature selection, which is the process of selecting the most important variables in the data and useful in machine learning, where the number of variables can be very large. So you need to reduce and find out the most useful or most important variables. And data visualization, by reducing the number of variables, it can plot high dimensional data into small dimension, make it easier for interpretation. And as I mentioned before, it can increase the signal to noise ratio by noise reduction. So by removing the lower principal component with low variance or low eigenvalues, which are assumed to represent the noise. And I will show you some example later. These represent or this can capture the real images or real contribution of the noise in a separate, as a separate principal component. And data compression. By representing the data using a smaller number of components, reduce the storage requirement and many, fast analyzing processing time. And also it can be useful to detect outlier detection. For example, in your data sample, there are some outliers, you can easily remove them. So this is kind of the imaging spectrum of the multi-wavelength fluorescent spectrum of a bacterial spore. So you can see different components, different chemical components in this spectrum. So, but the main problem is, whenever you do identification, all of the spectrum from the spores are very similar. It's very difficult to differentiate based on the pure signals or your naked eye. So you need some kind of machine learning to find out the very minute differences in the spectrum to differentiate. And PCA of the fluorescent data is used to establish some common relationship between spore samples. And individual species that many people are not aware of represent the spectral profile of the individual fluorophores in the sample and the noise. So many people use PCA as a classification technique only, but it can be used in many ways to identify even minute differences or minute fluorophores, for example, in the sample. So this is the simple way of representing the spore components and distinguishing species. So there are 3 species here, clearly differentiated, because in the naked eye it's difficult to differentiate. But here you can see 3 different species of bacteria is clearly differentiated. And here, as I mentioned before, the principal component 1 is captured the important fluorophores called tryptophan fluorophore in the bacterial sample. It's clearly, get out of the spectrum. In the previous spectrum, you see all the contributions. And the second one is the one called calcium dipiclonic acid, is a unique biomarker in the bacterial spores that you captured separately. And here the water Raman spectra, when you measure the fluorescence in a water liquid environment, you see the Raman spectrum is a unwanted signal. So here we eliminated Raman with the principal component 4. And as you know, bacterial spores are, sleeping stage, but whenever the conditions are favorable, it becomes bacteria. But when the water environment, you see the fluorescence signals are different. So we can clearly identify, and then we re-dry the sample and see whether that, the reciprocal treatment. And here you can see all the different environment, wet and dry states. You can clearly differentiate and characterize the samples using the principal component analysis. And ideally, the PCA actually, as I mentioned before, is decompose the EEM matrix, the excitation emission matrix, into different spectral components as different chemical components. So PCA combined with the spectral signature can be used to distinguish spore species in different environment. And you can see here, we actually did some simulations to see the peaks in a bacterial spores by using some simulation method. And then what we did is, as I mentioned before, after I discovered that after UV radiation, the fluorescent signal of the unique biomarker increased by about 30 times. That you can see here in the next slides. And also in the bacterial species, there are different strains of bacteria, strains of species. So one strain with the dipiclonic acid and one without dipiclonic acid. So you see the differences, very clear differences for the unique detection. And also here you can see the spores with DPA and without DPA. So you can clearly identify the differences. And also we wanted to see whether this enhancement is only in bacterial spores, not with other samples, other microorganisms. So we did experiments with all the available microorganisms in the environment and in the real world, and found only in bacterial spores that unique fluorescence enhancement. You can clearly differentiate other microorganisms from the bacterial spores. Again, I am showing here to identify the key component within the complicated structural analysis. So it's clearly identify the unique, the fluorophore. So as I will short down as the organizers asked to reduce my time. I think I am on time. So the conclusion is, fluorescence profile of a mixture of simulated chemicals are shown to correspond to the fluorescent profile, and changes in the fluorescence of spores after UV radiation is consistent with changes in the simulated chemicals. And we have found notable differences with the different species, and the fluorescence enhancement of bacillus spores can be caused by the UV radiation in the spectral region of EPA. So we found a unique way to detect the bacterial spores based on our findings. Thank you.
Thank you very much, Professor Sivanandan, for the insightful talk about the optical fluorescence imaging characterization of bacterial spores. And considering the time, let's skip the discussion session, but the speaker will be available during the lunchtime. You can talk to him over lunch. Let's move on to the appreciation event.
Now, I warmly welcome Dr. Mrs. Bharati Mayuradhan, Senior Lecturer, Computer Science, Faculty of Science, University of Jaffna, to introduce our final invited speaker.
Good afternoon all. On behalf of the VINGNANAM Research Conference Organizing Committee, it's my great pleasure to introduce the next speaker of this session, the final speaker, Dr. Thayasivam Udayasankar. Dr. Thayasivam Udayasankar is the head of the department, head of the Computer Science and Engineering at the University of Moratuwa in Sri Lanka. He leads data search, a research center focused on analytics, engineering, and data science. He earned his PhD in computer science from the University of Georgia in the US, and he has published over 350 research papers in respected conferences. The Sri Lankan government has awarded him the prestigious Iswami Awards twice for the tools and software he and his students developed. As the head of the open source organization, IVO, he offers systems, libraries, data sets, and tools for the data science and natural language processing. Dr. Udayasankar is also senior member of the IEEE. He has a strong interest and practical experience in advanced machine learning and data science, making him so expert in this fast-changing field. He has worked at well-known companies like Google, Microsoft, Ask.com, and Glassdoor, and he has also taught at the University of Moratuwa and other universities. Without further ado, I would like to invite Sir to deliver your talk.
While things are getting set up right, So we started this series of keynote with looking at the mess in a microscopic way. Sorry for over-promoting you as researcher, but just for the sake of the joke, please pardon me. And then came a powerful entrepreneur, wanted to track our packages, our items, even us. So he wanted to track our mess. And then came the zoologist, Dr. Nanda, scared the shit out of me because I adopted this urban lifestyle, moving from Jaffna way back in 90s after the displacement. And then came the doctor, Ganeshan, right? Sivanandan, and he said, wait, the mess is still sleeping. I'm going to talk about a very different mess here, and I know I have the best spot to talk today, like right before the lunch and rest of the talk. I was initially planned to keep it short, but the organizing committee told me that they are re-evaluating the lunch menu after listening to Dr. Nanda. So I've been told to fill the gap until they re-evaluate the menu. So I'm going to talk to you about the evaluation modality that is being adopted by the ML community and the mess that is happening there, right? So very briefly, but very, very profoundly, she has introduced me. Very thanks to for the kind introduction. And so, machine learning and AI is the buzzword, right? Like, as you can see, everywhere we are making impact, right? Any field is now data-driven, right? That's why people call nowadays modern day science as e-science, because every research paper in any domain you name is driven by data, and some machine learning or AI modeling is applied, and then boom, you have a paper. I did a quick study using some AI tools again, called Dimensions, right? And the number of publications in machine learning is growing exponentially, you can see. And out of that, the number of publications that is primarily based on the word accuracy and precision is also increasing and taking a dominant space. So, for computer scientists, if we can increase the accuracy or precision by just 1%, half percentage sometimes, we want to shout out to the world, say, we have the state-of-the-art model. So you mentioned the state of the art, right? That's then we have the state of the art. The next guy came and say, oh, I have the state of the art. Is it truly the state of the art? And look at the right-hand side now. Machine learning is, the keyword machine learning is slowly dying, and the keyword deep learning is now picking up. So if you put together, still the same accuracy and the precision game is what is played, right? Now, just for the audience who doesn't know what is precision and accuracy, the idea is like machine learning is going to predict. It's an astrology, new way sodara, right? Like it's like astrology, kind of, right? But data-driven astrology. Even astrology, to a certain extent, people claim data-driven. Let's not get into that debate. But machine learning is going to predict. It's going to say whether there is a cancer or not, looking at your, medical images or whatever, right? So some example like that, right? So recently there are some cases that deep learning is doing better than doctors. Like it's predicting cancer like even 15 years before it others can predict. So that's the latest updates are. So there are two things. So you predict correctly and you predict wrongly, right? So you could predict actual cancer person as a cancer person. It's one kind of correctness. You are predicting a non-cancer patient as a non-cancer patient, so another kind of correctness. There are two kinds of correctness. And other two are wrong, like wrongly classifying a cancer patient as a non-cancer, or a non-cancer patient as scaring him, now you have cancer, and threatening him, like he'll die even without getting a cancer if you predict that way. So that's the idea, and then based on those situations, there are metrics evolves like accuracy. That's the keyword a lot of students uses. Oh, mine is accurate, accuracy is high, true positive plus true, like both the correctness together. How much total correctness that you do over the total number of examples that are given. It's very simple, as like you're given some MCQ questions, how many correct answers you get, right? And if you want to split it like into two categories, then the precision comes and say how many correct cancer detection you did versus non-cancer. Like that's the precision angle. And then recall is the other metric. Let's not go too much into this mathematics, but I want you to look at this picture. This is a very popular picture, a lot of people now creating. An accurate and precise model is where you have the answers clustered together, but also in the center, right? But there are other models which is precise but not accurate, because you are like thinking about you are shooting gun, right, at a target. You keep shooting at a slightly slanted way, but you keep shooting at the right place. Still concentrated. That is the right-hand corner. That is precise but not accurate. Then you have like the left corner, like you are shooting all over the place. Like, you know, in Tamil, Kurudan, like they say, like you just randomly shoot, right? The right-hand corner is accurate but not so precise. You are around that, but not like cluster enough, right? So this is one thing I want you to sort of think about, why it is important to understand accuracy and precision together, right? A lot of people just bang on one metric and forget the other metric, especially in a lot of applications, both are important, right? But they'll only focus on one metric, that is accuracy, which is predominantly used, and then forget the rest. The other thing, before I go further, I want to establish a few properties. This is again supported by GPT-4. I created a list of machine learning model properties that is important to assess. One is predictability. That is what is measured by accuracy and precision, and a lot of us are banking on that. How accurate my model is. And that's the predominantly 90% of research is all about that. That is my estimate. You can't quote on that. There is no hard study. My estimated 90% is around that. Right? Then come performance. There are machine learning models that can do accurately, but is it fast? Because nowadays we are looking at a machine learning model that we can actually embed within this, even probably within your chips in the future, right? So edge computing is evolving, and we wanted to keep it simpler. And then robustness. Can it really withstand the changes around it, right? So we want to build a model that sounds to work good. We have some students who like do very well in exams and etc. You graduate them and put it in industry, there comes a problem. Right? So can they really withstand, right, the models? Then come generalizability, then come explainability, fairness, that's very important, that is growing nowadays. We want our model to be fair. Is it inclusive of all kind of problems? That's very, very important in machine learning nowadays. And scalability, can really scale well, because that's very important. You put out into production, and then as your business increase or demand increase, can it really scale well is very important in machine learning. Then stability. And then adaptability is there. Can it adapt to various situations? Can this be used for others? There's multi-usability of it. Resilient to data drift. This is the very hot topic, MLOps nowadays. A lot of engineers are required. Many people are not there in it. Is that, can a model actually adapt when external environment change, right? You build a model assuming this is how, our environment is going to be. For example, you build a mobility model, how people are moving, or before COVID. Will it withstand when COVID kind of situation happen? Or if the population increase or your demand has changed, it won't. So if there is, can a model withstand external changes that is happening is another topic evolving, like very hot topic nowadays. And we look at machine learning models to do good in all of this, right? And finally, it comes to usability, right? So there is one famous scientist called Box from London, right? A statistician. He said, none of the model is good, none. But some are useful. The question comes down to the fact, what you are building, is it useful? As you rightly said, sir, if you can find a solution that is useful for the community, they are boom, $1 million business. Otherwise, nothing comes out of it. So there is one other thing I see, a lot of researchers are just simply reporting one experimental results, right? Oh, I tried in this test data, I got 92.5% accuracy, and they forgot to report a cost-validated results. Cost validation is fundamental, and I see that a lot of research papers coming out without mentioning the cost-validated results. Second, when you mention the cost-validated results, it's also important to look at the error bar. Because sometimes it may look like the other guy is performing slightly higher than you, but with a large error bar, no point, no use. Right? So is it statistically actually different, making a difference when you say you have a model that is better than the other guy? Right? This is very problematic, and I think this is growing problem even in some of the international reasonably reputed journals. I mean, if you go to like really top tier, then it's a different story. But then in most of the other places, this is a problem. And I see even in top tiers, just for the sake of keeping apple to apple comparison, just stick to the same data set. They don't do cross-validation anymore, right? So there is sort of a game we play in numbers instead of making a real impact in machine learning. I see it as a growing concern. And I wanted to let you know that this is an extract from a slide. I normally do a training for executives. How do you pick your data science team or data science application or model? This is sort of coming from that angle. How do you really pick a right solution for a machine learning solution? Right? So just keep in that angle as well, not like only publication angle alone. Now next is that class imbalance. A lot of people, my simple question is that there is a cancer detection test with accuracy 99.9, right? A cancer detection test for a very, very specific one, difficult cancer problem has been built. It is reported 99.9 accuracy, but still got rejected. Why? Any guesses? Very simple, right? Like if you have a cancer that occurs in the population only 1 in 1,000, right? It appears to 1 in 1,000 persons only. And if your test is simply going to say nobody has cancer, for everybody that you put into the test, no cancer, no cancer, no cancer, it will still be 99.99 correct. You just need to detect that one guy. So this is the wrong measure. So I see sometimes people overlook what right measure to use, just simply follow like what everybody else is using, right? So this happens a lot of time when you have a class imbalance. So you can't simply bang on what is just being used. There's other question, right? There are two models with same accuracy. One is preferred over the other. Why? So there are two models. Both of them have the same accuracy, right? One is preferred over the other. Why? Well, you look into confusion matrix and realize both students got 90 marks. But this guy actually made 10 mistakes this guy made are made in either tough questions or maybe his mistakes are near to the right answers. Right? In MCQ, like you may not be easily say, but in machine learning and multi-class we can still do. If you look at the other guy, the blue guy, he's making mistakes, but his mistakes are like, he's even making easiest mistakes. So there are ways that you can understand the model better by going to the confusion matrix. And these are simplest tools, right? This has been there for a long time. But I see a lot of research publications and students' projects that people simply purely bang on that number, not even don't want to go to the secondary analysis, questioning what is in front of you and figuring out, is it really what it is? The next question is, right, there is a new other problems that is evolving. Like for example, robustness is very important nowadays, right? There are machine learning models that is built, right? Those who know image processing nowadays, machine learning models can detect the image, object in the image very accurately, like really good job at it. But people found out a way to cheat it. They took a panda image, they added a slight noise to it, systematically generated noise to it, and gave to that model. It said it's a gibbon. So it's known as adversarial attacks, like similar to how you attack people's website and other things. We can now attack even machine learning models, and we can figure out how to cheat it. Now this will become a bigger problem, right? If it will become a bigger problem if hackers find a way to hack online financial analytical models, online, it will be a big money loss, right? Online customer profiling models. Then you can cheat and get some discounts that you are not supposed to get, and many other things, right? So that is one thing that we are interested, can machine learning model really withstand such attacks, right? Noise, outliers, missing values, these are standard stuff. Drift, as I told you, that is the emerging concept of building online learning where you already learn a model, deploy it, and it keep learning in the real time, right? That's the new thing that is MLOps is focusing on, reasonably under-researched topic, and a lot of people are focusing on. And as I said, like the simplest way to test it is like you take the test data and do some modification and then supply it and see, can it really work, right? Also, just wanted to just quickly tell you, like it is always the simplest solution is always better. That's what Arkham said. Like it is known that simpler models tend to be more robust than complex models. Like everybody nowadays, my students want to do deep learning projects. Any solution, any problem that you put in front of them, they want to do some sort of they take an LLM, fine-tune it, and try to solve it. Don't do that. Don't do that. In fact, there's a study that proves that 80+% of your corporate problems can be solved just by descriptive analysis, right? So why you want to do machine learning if there's no need, right? So then scalability comes. Can your model really scale right? With like if you give more CPU power or memory power or more data, can really increase well with it. So there is a model that is built with 1 billion data. Now you give 1 more million data, it can really improve the accuracy, or it's just going to stay alone. Right? That's the key differences nowadays we are looking at, not just simply beating the accuracies anymore, right? And so scalability is usually you are giving some resource that can be, as I said, like computational power or data or many other things, and you're looking at a performance metrics and see the trend. That's the scalability is in general. What kind of trend that your model is performing? Linear, perfect. Some sort of a logarithmic saturation, even better. Negative, so bad, right? Negative scalability is so bad. And you can see that the next thing is interpretability, like machine learning model will tell you a decision, but if you can't tell, like, a customer walks into a bank, your ML model said don't give him loan, you say that, oh, sorry, our model said I can't give you loan. No, not no. You had to tell the customer why he is not getting a loan. That's very, very important these days, right? So that explainability is another thing, like especially with neural networks and deep learning, you can see that is on the top side, explainability is really low. They perform well. Their model accuracy is high, but the explainability is really low. Now there are new researcher, that is trying to solve that, trying to shift them to the, to right-hand side while keeping the accuracy high. But that's other thing I want you to understand is, can your model explain is also very important thing. Final point is fairness. Fairness is machine learning is very interesting. Like for example, I'd like to bring you one example that there was a study that proved that if you have a face detection, most of the face detection algorithm does not work well with colored faces. It works well with white people, but no. There's other fairness problem in LLMs, right? Image generators, now they solve to a certain extent. If you go and ask, like, can you draw a professional, like, that modern day AI can draw pictures for you. You go and ask, can you draw a professional person for me? It is most likely going to draw a white man. So that means there is a bias problem. It's not fair. Right? And most of these natural language, which is my area of interest, that most of the NLP models that we build are Eurocentric, not only NLP, image model, Eurocentric. English language, English culture and around. It doesn't have the nuances and adaptability of various other languages and cultures. That's becoming a bigger concern and problem nowadays. And we are actually looking for, my friend Sarvesaran is here, we used to work together in that area, that we are looking for ways to create data set in our languages to see like how our LLMs actually work with our culture. Can it really, like, is it sensitive to culture? How sensitive is very important nowadays, right? The other one is disparate treatment. That is, you are treating not equally for both the parties. And another problem is that sometimes your machine learning model will be oversimplified, right, or more generalized towards a high population than the smaller population. So there is a rule of thumb is that 80% of rule is often used to measure disparate impact. If the selection rate for a protected group is less than 80% of the selection rate of the high performing group, the process is said to have disparate. So now, this is the rule that is now US is following as a rule of thumb to avoid disparity in your model. So again, if you are building a model for public audience or wider audience, fairness is very important, and there are metrics relevant to it. I'm just going to skip what specific metrics just for the sake of the time, and the menu seems to be prepared as well. In final conclusion, I want you to understand, like, it's not about like learn to shoot at the middle of the your target. It is about can you shoot through it, the impact, right, and also whom you are shooting. Right? It's just an analogy. The whole point is that ML models, right, predictability is what a lot of people are focusing on, and then a little bit of robustness, and then scalability. Explainability is evolving, and new topic, fairness, very well under-researched. So when you build models, please look at it in a 360-degree and see whether your models fits all the angle, and that will really make an impactful research. Thank you. I hope I am well in time.
Thank you very much, sir, for your insightful talk. Due to the time limitation, we will skip the question and answering session. If you have any question, you can ask during the lunchtime. As a gesture of the appreciation, we will have a small token of appreciation. Please accept.
At this time, we would like to take a moment to recognize and sincerely appreciate the contributions of people who have played an instrumental role in making this conference a huge success. To deliver the vote of thanks, I now invite Dr. T. Kogul, Secretary, Vinyan Research Conference 2024, to the stage.
Thank you. So, good afternoon, ladies and gentlemen. As we conclude this enlightening inaugural session of VRC 2024, it is my privilege as the conference secretary to extend the heartfelt vote of thanks to everyone who contributed to this success. First and foremost, I express my sincere gratitude to our esteemed keynote speaker, Dr. Suthanandan and Dr. Sabeshan, for sharing their groundbreaking insights. Your contribution has truly set the tone for the rest of the conference. A special thank you goes to our invited speakers, Dr. Nanda Nandakumar, Dr. Shivanandan, Dr. Udaya Sangar, for their thought-provoking presentations. Your talks have broadened our perspectives and sparked meaningful discussions. We deeply appreciate your willingness to travel from abroad at your own expenses, demonstrating remarkable dedication to this field and this event. I also extend my sincere gratitude to our Vice Chancellor for joining us today and for providing invaluable administrative support. Your presence and guidance have been a great source of encouragement, and we are truly grateful for your ongoing support in making this conference a success. We are honored by the presence of our guests, including deans of other faculties, esteemed council members. Your support and participation elevate the significance of this event, and we sincerely appreciate your time and contributions. My deep appreciation goes to our conference chair, Prof. Nobel Surendran and Prof. Ravi Rajan, for their leadership and guidance. Your dedication has been instrumental in bringing this event to life. I also extend my gratitude to the session chairs, Prof. Vignaruban, Prof. Shyamalan, Prof. Ishwara Mohan, Prof. Meena Sendil Nandanan, and Dr. Mrs. Mayuradan for expertly guiding the session and ensuring seamless transitions. Special thanks to the technical session chairs who will contribute this evening sessions, Prof. Christy Jayasilan, Dr. Mrs. Sivaruban, Prof. Jayadevan, Dr. Varadan, and Prof. Angran. Thank you all. A sincere thank to BC Media for the excellent coverage of the conference. Your efforts in capturing the key moments have preserved the memories of this special occasion, and we truly appreciate your contribution. I would like to thank this opportunity to extend our heartfelt gratitude to our sponsors, the National Science Foundation of Sri Lanka and the Norwegian Directorate for Higher Education and Skills under the project. Your final support and partnership have played a crucial role in making VRC 2024. I extend my heartfelt thanks to our librarian for kindly providing the library auditorium as a venue, and to the library staff for beautifully decorating the auditorium and the tables. My sincere thanks also go to the head of the physics department for providing the space for our technical session and lunch, and to the head computer science for providing the laptop for technical sessions. Your collective support has been instrumental in ensuring the smooth functioning of this conference. Also, I offer my heartfelt thanks to Dr. Mrs. Sandra Kumar for overseeing all the financial activities of this conference. Also, our appreciation goes to Dr. Amal Raj for managing the release of conference proceedings. Your meticulous work ensures that the knowledge shared here will reach far beyond this auditorium. Also, a special thanks for Prof. Ramanan for carefully proofreading the proceedings and preparing the mementos. I extend my sincere thanks to all the reviewers for the valuable time and effort for reviewing the conference abstracts. Your evaluation and constructive feedback have been the key in maintaining the quality of our conference. A special thank you, Prof. Shyamalan and his team for maintaining the website. I also extend my special gratitude to Mr. Thiliban for his creativity in designing the flyers, banners, and other graphic materials. Also, to Mr. Harichandra for his excellent work in designing the certificates and ID cards. Also, our thanks goes to Dr. Sudhasini, the technical program chair, and her team for the exceptional leadership and coordination. Also, our sincere thanks goes to Dr. Sribaran, Dr. Manjeevan, and their team for the excellent work in the logistic committee. Your efficient coordination and behind the scene efforts have been instrumental in smooth running of this conference. As one of the joint secretaries, I offer my heartfelt thanks to my fellow joint secretaries, Ms. Sudarsini Satyaruban, for her support and collaboration in coordinating all the activities. Finally, I would like to acknowledge the efforts to the entire organizing team and volunteers who have worked tirelessly behind the scenes. Your commitment and hard work have not gone unnoticed. To all the participant attendees, thank you. Your presence and engagement make this conference meaningful and successful. If I have unintentionally missed thanking anyone, please accept my sincere apologies. Your contributions are deeply valued, and we truly grateful for your support in making this event a success. Before we conclude, I invite all the registered participants and guests to join us for the lunch, which will be served at the physics department. We look forward to continuing our discussion in more formal way, and we hope you enjoy the meal. Thank you very much. And the speakers and the guests, please come to the front to take a photograph. And others, please go to the lunch, and we will join back at 1:30 p.m. Thank you very much.